us to arrange more such programs to enrich the young minds in the new academic scenario. Lord, we ask everything in the name of our Lord Jesus Christ. Amen.
Amen. So any program will never be a success if it has not been led by the correct person. So American College has a very good leadership under Dr. M. Dhavamani Christopher, our principal and secretary. So I request now our principal to inaugurate this day's program with his kind words. Principal sir, over to you.
Good morning.
Morning, sir.
Can you
Morning,
hear
sir.
my voice?
Yes, sir. Please.
Thank you, sir. Thank you, sir. A webinar on spectroscopic techniques. Congratulations to the Director of American College Central Instrumentation Center, Dr. Jemima Balaselvi Juliana, who is also the convener of the webinar, and the co-conveners, Dr. Nazira Banu and Dr. Jansrani, and thanks to the resource persons, Dr. Radhakrishnan, Chief Scientist, CSIR Sigri, and Dr. Saravana Kumar, Technical Officer, CSIR Sigri, for accepting our request to be the resource persons. Friends, the coronavirus disease is an infectious disease caused by many discovered coronavirus, the newly discovered one. WHO published the first disease outbreak news on the new virus on 5th January 2020. The same WHO announced that COVID-19 can be characterized as a pandemic on 13th March 2020. Entire world kept after the 13th March 2020. No one knows what to do, but we have to find out how to overcome these kind of hurdles and problems that the entire community expecting now. Anything, we have to take it in positive sense. We have to adapt ourselves for any situation. God gave a chance to think about our future. Yes, it's a God-given break in the fast and furious and mechanical world. This is an exercise to all to face tomorrow's world. So let us all face boldly this situation. In this kind of situation, many departments in our college came forward to conduct webinars, workshops, conferences for the benefit of their students, their faculty, and also to the researchers and public. Likewise, the newly established American College Central Instrumentation Center is organizing their second webinar on spectroscopic techniques through Zoom with apt persons. The whole academicians are focusing on online education nowadays. I do appreciate the efforts of American College Central Instrumentation Center for organizing such a useful webinar, second in a row. And they have their third and fourth on tomorrow and day after tomorrow also. Central Instrumentation Center is an collective science laboratory situated in our college. For any kind of research activities, you can make use of the Central Instrumentation Center. I think this is the only college having Central Instrumentation Center in Arts and Science College level in Mary Kamaraj University region. Request all our friends to make use of the facilities. For any details, you can contact Dr. Jemima. Friends, I'm happy to inaugurate the webinar on spectroscopic techniques organized by the American College Central Instrumentation Center to their students, researchers, and public during the lockdown period caused by coronavirus pandemic. About our resource persons, Dr. Radhakrishnan, the chief scientist from CSIR Sigri, who has PhD in physics with more than 30 years of teaching experience, has published 24 international publications and completed many projects, and he visited Myanmar and Germany. Also, we have Dr. Saravana Kumar today, who has PhD in chemistry, technical officer from CAF and SCAIF CSIR Sigri. He is a FDA approved technical person and full member Quality Council of India with more than 15 years of teaching experience, with 3 publications and 2 patents. It's my pleasure to thank again the resource persons for accepting our request. Hope it will be useful for all. Once again, I congratulate the Director of American College Central Instrumentation Center, Dr. Jemima Balaselvi Juliana, co-conveners Dr. Nazira Bano and Dr. John Sirani for their wonderful initiative. God bless.
Thank you very much, sir, for your kind words. Now I hand over the session to Dr. Nazira Banu to chair the first session.
Good morning, everyone, and welcome to today's session. This is the day that the Lord has made. Let us rejoice and be glad in it. First and above all, I thank the Lord Almighty for being with us throughout the entire session. I would like to thank our Principal and Secretary, Barzar, and Director, ACCIC, for providing American College Central Instrumentation Center facility. It is a great pleasure for me to introduce and welcome our speaker, Dr. S. Radhakrishnan, Chief Scientist, CSIR, Central Electrochemical Research Institute, Karaikudi, who is going to talk about basic principle and applications of NMR spectroscopy. He has completed his PhD at Madurai Kamaraj University, and also he has completed advanced training program on NMR spectroscopy measurement techniques at Germany. His field of specialization is analytical spectroscopic instrumental techniques with more focus on NMR spectroscopy. He has more than 30 years experience on instrumentation and research. He has handled several projects and published more than 24 papers in international journals. He's a member in many institutional committees and also led a 3-member team to Myanmar under Indo-Myanmar program. Once again, I welcome Dr. S. Radhakrishnan to deliver his speech. Thank you. Welcome, you, sir.
Thank you, Dr. Dharmani Christopher, for the nice introduction. A very good morning to everyone, one and all. On behalf of Central Instrumentation Facility, Central Electrochemical Research Institute, I extend a warm welcome to all the course participants. At the outset, I would like to thank Management American College and the Department of Central Instrumentation Center faculties, and in particular Dr. Nazira Banu and Dr. John Sirani for the invitation, opportunity, and the coordination. Thank you, ma'am. Our central instrumentation facility details are available in the. Am I audible, madam? Am I audible?
Yes, sir. Yes, sir.
Yes.
I shared my slides, sir. The first slide,
Yes, sir. Your slide is visible, sir.
Okay, okay. Shall we go ahead?
Visible.
Yeah, yes, sir.
Okay,
Thank you.
okay.
Proceed.
So our central instrumentation facility, I am heading the central instrumentation facility of our institute. Our central instrumentation facility details the charges, the facilities available, and what are the formalities for submitting the sample, outside sample, all are available in the website www.cv.west.in. Right? And in this central facility, we have 2 NMR spectrometers. And this is the so this is the superconducting magnet. This is the 400 megahertz NMR spectrometer, and this is the superconducting magnet. This they call it as a console, which houses all the electronic modules, and through this tabletop, we control and monitor the entire spectrometer operation. And there is a powerful NMR software. They call it as the Bruker company. They call it as Topspin. They name it as Topspin, through which we can acquire and process the NMR data. And this is our 500 megahertz NMR spectrometer with auto sampling features. This is superconducting magnet. This is the auto sampler. This is the main console. And we can load 24 samples at a time and you can go first. Through net, you can control and monitor the spectrometer operation sitting at any place in the world. This we are using it for solution NMR, liquid state NMR. The other one we use it for the solid state measurements. This is the latest one available, the highest model, high-end model available in the world. 1.1 and 1.2 gigahertz. It means 1,200 megahertz NMR spectrometer available in the world from Bruker, Germany. It's around 25 to 30 crores. And this is the low-end model, tabletop desktop model available, is around 80 megahertz with the limited features. And the cost comes close to, this type of small model itself comes close to 1 crore rupees. So what NMR can do for us? Basically, it is a tool, a technique. One of the analytical techniques, spectroscopic technique, is a non-destructive, non-invasive technique for the structural elucidation of molecule in one sentence. In its simplest form, NMR allows identification of individual atoms in a pure molecule, much like FTIR spectroscopic technique identifies the functional groups. NMR spectrum tells us the user about the atomic environment. For example, in the case of 1H, CH3, CH2, CHO, COH, CH2Br, CHBr2, etc. Different kinds of environment it tells. And in some cases, how many atoms in each type exist within the sample. And is based on quantum mechanics. As such, it is more reliable, dependable, predictable, and reproducible. One of the important spectroscopic analytical technique available. Based on spectroscopic technique. Spectroscopy, we all know, deals with the interaction of electromagnetic radiation with matter. Matter means your samples, which are in the form of solid, liquid, and gaseous state. And electromagnetic radiation travel at the speed of light in the form of wave as shown in this figure. This wave carry packets of energy. While traveling, carry packets of energy as per quantum mechanics. They call it as photon. The energy of the photon is given by E equal to, the energy of the photon is E is given by H, Planck constant, F is the frequency, which is also equal to hc by lambda. C is the speed of light, lambda is the wavelength. So in all this spectroscopic technique, you have the electromagnetic radiation interacts with the sample differently because the energy content is different and it produces different forms of output. Based on the output, they have been categorized as gamma ray region, X-ray region, UV, visible IR, and the radio region of the spectrum. The entire spectrum is like that. Of these, you know very well, gamma ray, X-ray, and UV are high energy, others are low energy region. So each region interact and some region, for example, UV, play only with the outermost valence electron, and X-ray, they play with the innermost acacial electron, etc. IR vibration spectroscopy, and radio region falls in the magnetic resonance spectroscopy. So in all these spectroscopic technique, one common thing is that the sample absorbs energy when the condition matches. What is the condition? The energy gap delta E equal to H into frequency. What is the energy gap? As per quantum mechanics, the energy levels are quantized. In the case of electron, energy levels are quantized in SPDF orbitals. Like atomic energy levels are quantized. Like magnetic energy levels of the nucleus is also restricted to certain discrete values, permitted values. So NMR is the transition between these two permitted magnetic energy level transition. Delta E equal to U1 minus U2. This is the basic of the NMR, magnetic energy levels. Not the electronic transition or vibration energy transition. This is the magnetic energy level transition between the two permitted energy levels of the atomic nuclei. NMR spectroscopy is a branch of spectroscopy, one of the branch, low energy region of the spectroscopy. Low energy meaning radio frequency region or radio region. In that region, energy is low, E equal to h and f. F is small. It means it has got high wavelength. So it's a 100 years old story. NMR is a 100 years old story. Way back in 1902, a Dutch scientist, Zeeman, performed an experiment. He put an atom, or a molecule inside a powerful magnetic field, and he observed a split in the spectral length, split in the atomic energy levels. Consequently, there is a splitting in the spectral length. Basically, splitting in the atomic energy levels. That splitting is called Zeeman splitting. That effect is called Zeeman. This is the starting point. Splitting of the energy level under the influence of external magnetic field was successfully demonstrated by Zeeman. The splitting is called Zeeman splitting. So after 50 years, two different groups, Professor Bloch and Professor Purcell, detected weak NMR signal, detected very weak NMR signal from a sample. So a sample is 1 kilogram of paraffin wax kept inside a magnetic field. Not 1 gram or 100 grams, 1 kilogram of paraffin wax kept inside a magnetic field. They constructed a crude NMR machine for which they shared the Nobel Prize in 1952 under physics category. So far, this technique has won several Nobel Prizes for various discoveries. The last one was in 2002 for discoveries concerning MRI, magnetic resonance imaging. So this itself speaks about the importance of this technique. Very, very important analytical spectroscopy technique. Now, we move on to the NMR basic control. It exploits the magnetic property of the nuclei. Nuclei behave like a small magnet, tiny magnet with a bar magnet, as shown in this figure. We all know atom consists of nuclei, which houses both proton and neutron. Proton, neutron, and electron are elementary particles. These elementary particles possess mass, charge, and location, as well as in addition, they possess one more quality or one more property called spin. What is spin? What is charge? What is mass? They are all inherent property of these elementary particles. By birth, these elementary particles acquire this property, mass charge. Like spin is also an element, fundamental property of this nuclei, these fundamental properties of proton, neutron, and electron. These proton, neutron, and electron are imagined to have spin on its own axis. Imagined to have spin on its own axis, as shown in this figure. So, as a result, they possess a corresponding property known as spin or spin angular momentum. Corresponding property, since it is imagined to have spin, be it a positively charged proton or negatively charged electron. If it charged spin, it possesses a property called spin or spin angular momentum. Momentum we all know. A mass moving with a velocity, then it is called, mv is called the momentum, that is linear. A spinning charge, be it a positively charged proton or negatively charged electron, generates a magnetic field as shown in the figure. Generates a magnetic field as shown in this figure. This is the magnetic spinning charge produces a magnetic field, and its resulting magnetic it behaves like a magnet. Dipole magnet. Dipole means two poles, north pole and south pole, like a bar magnet. So magnet has got many properties. What are the properties? Magnetic susceptibility, permeability, magnetic moment, many properties. So we are concerned only with this magnetic moment property of the magnet. This is the elementary particle magnet. This has been designated as mu. Why this magnetic moment is important? because the magnetic resonance spectroscopy is the study of interaction of, rather magnetic interaction of these proton, neutron, elementary particles with the external powerful magnetic field. How they interact with the external powerful magnetic field. If we, what is magnetic moment? You bring two magnets together. The tendency of one magnet to align with the other, the mechanical force, the torque, is called the magnetic moment. So that is why, among other magnetic properties, this property is very important from nuclear magnetic resonance point of view. So proton, neutron, and electron behave like a small magnet, small tiny magnet, small magnet, small tiny magnet. So it has, since it is spinning, it has got a spin angular momentum. As per quantum mechanics, scientists have assigned some spin value or spin quantum number I equal to half. Proton spin is half, neutron spin is half, electron spin is half. And this have its unique magnetic moment value, which is proportional to the spin or spin angular, directly proportional to spin or spin angular. The table shows the magnetic moment value or unique value, magnetic moment value of this elementary particle, proton, neutron, and electron. So with this idea, we move on to the next step. So as I told you, the magnetic resonance spectroscopy is the study of interaction. Magnetic interaction of these elementary particles with the external, how it interacts with the external magnetic field. If we talk about electrons, how it interacts with the external magnetic field, then the branch of science is called electron spin resonance. If we discuss the whole nucleus as a whole, which consists of both proton and neutron together, how it interacts with the external magnetic field is called nuclear magnetic resonance spectroscopy. Why we consider the nucleus as a whole? The nucleus has been viewed, atomic nucleus has been viewed as a positively charged spinning sphere. Why positively charged spinning sphere? Proton is a positively charged particle, neutron no charge. That is why the atomic nucleus has been viewed as a positively charged spinning sphere. So if any charge, the physics theory, if any charge spin, it behaves like it produces its own magnetic field and behaves like a magnet. That's why the nucleus has been considered as a small, tiny magnet, permanent magnet with a bipole. Both poles are the north and the south pole bar magnet. So with this idea, we move on to the next. So atomic nuclei, each and every atomic nuclei, hydrogen, oxygen, sulfur, it behaves like a small, tiny magnet with its own spin value and its unique magnetic moment. The spin value and magnetic moment originate from the of the proton and the neutron. We have to derive the spin value from that of the proton and the neutron. How we are going to derive the spin value of the nuclei? Let us take one few examples. Hydrogen atomic nuclei. How many protons are there? Only one proton. Number of neutrons? No neutron. What is the spin value of a proton? Is half. So the spin or spin quantum number of hydrogen atomic nuclei is half. Let us take carbon. Number of protons 6. Number of neutrons 6. Like electron, these proton and neutron occupy in different shells. In a shell, the protons pair with each other and neutrons also pair with each other. So the spin value, how many unpaired protons or neutron or nucleon available in the atomic nuclei give rise to the spin of the particular nuclei. Here, the number of protons is 3 protons pair with another 3 protons. So unpaired proton is 0. Like 3 neutrons pair with another 3 neutrons. Unpaired neutron equal to 0. So the number of unpaired proton and unpaired neutron equal to 0. The spin value is 0. It means that there is no spin quantum number, there is no spin angular momentum. This nuclei is spin inactive. We cannot detect this nuclei from the NMR. It won't give rise to any NMR signal. Rather, it's isotope. 13C nuclei. Number of protons 6, number of neutrons 7. we are left with one unpaired neutron. What is the spin of the unpaired neutron? Half. So the spin of this carbon atomic nuclei is spin half. So what we are detecting carbon NMR is that of the carbon 13 nuclei, not from 12C. 12C is an NMR inactive. Let us go to one more example, nitrogen 13. Number of protons and number of neutrons, 7, 7. We are left with one unpaired proton and one unpaired neutron. So proton spin equal to half, neutron spin equal to half, half plus half, we are left with the nitrogen atom, nitrogen atomic nuclei spin equal to 1. Like we can derive the spin value of each and every atomic nuclei. But what the thumb rule says, the number of protons and number of neutrons equal and even. For example, 12C, 16 move, spin equal to 0, NMR inactive. Whereas the number of protons and number of neutrons equal and odd, for example, 14N, then its spin value is 1. Whereas the number of protons and number of neutrons in the odd even or even odd ratio, like 1H, 19F, then the spin is half or integral multiple of half. Integral multiple of half means 3 by 2, 5 by 2, 7 by 2, 10. So what is the signal? We know the magnetic moment. So the magnetic moment, when you put the sample inside the external magnetic field, it interacts with the external magnetic field. What is the significance of the spin? Spin decides the number of magnetic energy levels of the atomic nuclei. If magnetic energy levels are there, then only the transition will take place. Absorption of electromagnetic radiation and the subsequent transition will take place. For example, spin 0. So as per the equation, how many energy levels are possible is decided by this equation. 2I plus 1 energy levels are possible. Magnetic energy levels of the atomic nuclei are possible. Spin 0 nuclei, 2 into 0 plus 1 means only one spin level. Only one spin level means delta E equal to 0. Delta E equal to 0 means these are all NMR inactive. Let us take spin equal to half. 2 into half plus 1, which is equal to 2. So there are two possible spin levels. One is called lower energy level and another one is called the high energy level. It's NMR active. So spin 3 by 2 means 4 energy level, 5 by 2 means 6 energy level, etc. etc. But please note, the transition will take place only between delta E. So it cannot take place between 2 delta E or 3 delta E in the case of this spin 3 by 2, 5 by 2 nuclei. These nuclei, spin 3 by 2, 5 by 2, and 7 by 2, etc., are called quadrupolar nuclei. They give rise to broad NMR signal. Now, so we know the atomic nuclei possesses spin angular momentum or spin quantum number is unique value and it's a unique magnetic moment. Now we have to see the interaction of this nuclei magnet with the external magnetic. That is basically about the magnetic resonance spectroscopy. And this is our sample tube. We take some sample. Nothing but take water, simple molecule H2O. Tap water also, you can take it as a sample. So the simple the NMR tube. NMR tube is made out of some special glass, 5 mm outer diameter, and 7 inches in height. We need for about 1 ml, maximum of 1 ml of sample. Take some tap water and keep it inside the powerful magnetic field. This is the superconducting magnet, very powerful magnetic field of few Tesla. The magnetic field axis is in plus Z direction as well as in the, it has been constructed that way. It is in the plus Z direction and minus Z direction. The sample, I am going to put this sample through this and inside the powerful magnetic field. What are the interaction? What is the consequence of this atomic nuclei with the external powerful magnetic field? So obviously we expect split in the energy level and some other things, absorption of electromagnetic radiation and all. We will see one by one. First thing, the moment you introduce the sample, there will be an interaction between the atomic nuclei, because this is a magnet, small tiny magnet. As shown, these are all atomic nuclei, hydrogen atomic nuclei and oxygen atomic nuclei. These are all small tiny bar magnets. So there will be an interaction between these atomic nuclei with the external powerful magnetic field. So how many molecules are there? As per the Avogadro number, there are millions and millions of molecules in 1 mole of water. Millions and millions of hydrogen atom, millions and millions of oxygen, like millions and millions of this kind of nuclear magnets. You see the orientation, when there is no magnetic field, they will have all possible orientation. So the net magnetic moment, if there is no field, external influence is zero. The moment you put the sample, they will align with the external magnetic field. If you bring two magnets together, north pole of one magnet will align automatically, two bar magnet will align automatically with the south pole of the another magnet. Here too, the magnetic field axis of the external magnetic field is plus Z and minus Z. So the nuclear magnet, some will align with plus Z axis, the remaining will align along the minus Z axis of the external powerful magnetic field. Just for our simplicity, there are 100 molecules only. 50 will align with the plus Z, and rest 50 will align with the minus Z with almost equal population. I am using the word now, almost. I am not saying equal, almost equal population. The one which align with the plus Z axis is called high energy level. The one which align with the minus Z, nuclei align with the minus Z axis is called low energy level. There is a split in the energy level. Split in the energy level. This state is also called beta state and alpha state. The different nomenclature in different books. The energy level split has occurred by the application of external powerful magnetic field. Now, I used the word almost equal population. If there is no population difference, there won't be any absorption, electromagnetic energy absorption, and there won't be any absorption and there won't be any signal. So, what Professor Boltzmann suggested, there is a slight excess population, slight excess nuclei in the lower energy level, in order for any system to be in thermal equilibrium. How much excess is there? If you apply a magnetic field strength of 2.35 Tesla, 2.35 Tesla per million, there is an excess of only 16 atomic nuclei. This 16 excess nuclei will absorb radio frequency and it will go to the higher energy and give rise to NMR signal. That is why the phenomena, NMR phenomena is itself is a weak phenomenon. We will get a weak NMR signal. That's why we have to repeat the experiment that they call number of scans many times. How to increase the population frequency? One way, by increasing the magnetic field strength. I have increased by 4 times, 4-fold. Again, it has increased only 64. Again, I increased another 2 times. Again, increased to 2-fold. This is one way. By going for higher and higher magnetic field strength, NMR spectroscopical measurement technique, but it's a costly affair. And what is the equation says that the population difference N1 by N2 between the lower and the higher energy level is proportional to delta E. Delta E can be increased by increasing the magnetic field strength. Another way, it is inversely proportional to the temperature. By decreasing the temperature, we can keep the sample at a lower temperature. So we can go up to 4 degrees Kelvin using some cryoscope. Simple way is by increasing the concentration that is in our hand. Right? Now, first thing is the split in the energy level that has been taken place by the exposure of the external powerful magnetic field. As I told you, the moment put the sample inside the magnetic field, there will be an interaction between the external powerful magnetic field and the internal atomic nuclei with a magnet. If you bring two bar magnets together, immediately they will align. North pole of one magnet will align with the south pole of. It's not a bar magnet. It is there. It's a spinning. It's like a bar magnet, but it is a, we call it as a spin. It's imagined to have a spin on its own axis. So in that process, in the aligning the outside magnet, external magnetic field is a very powerful magnet. 9.4 Tesla, 10 Tesla, 11 Tesla, etc. Internal nuclear magnet is very tiny magnet. So external magnet dictates the internal magnet to align with its axis plus Z and minus Z. In the process, it starts to proceed around the magnetic axis, plus Z axis and the minus Z axis. The one which in the higher energy state will proceed around the plus Z axis in the anti-clockwise direction. The one, the nuclei, the number of nuclei, which is in the lower energy state, proceeds around the minus Z axis in the clockwise direction, as shown in this figure, like tau. At what frequency? At some frequency, characteristic frequency. That frequency is also called resonance frequency. The frequency is also called Larmor frequency. So the resonance frequency is given by the expression mu, magnetic moment of this atomic nuclei, V0, the applied magnetic field strength, V0 divided by H Planck constant, I is the spin or spin quantum number of the nuclei, atomic nuclei. See, you could see this plot. This plot, there is a plot of four different nuclei whose spin value or spin quantum number equal to half. Hydrogen, fluorine, phosphorus, and C13 all have spin I equal to half. So they are exposed to the external magnetic field of 2.35 Tesla. See the resonance frequency of hydrogen atomic nuclei, 100 megahertz. 100 into 10 to the power of 6 times per second. Whereas fluorine resonates at 94 megahertz, phosphorus 40 megahertz, and carbon around 25 megahertz. So each and every atomic nuclei has its own value of magnetic moment. Rather, it interacts with the external powerful magnetic field differently, and it gives rise to its own characteristic resonance frequency. So the highest frequency is that of the hydrogen atomic nuclei. So the NMR has been designated by the frequency, highest frequency possible, not by that of the magnetic field. The highest frequency is that of the hydrogen atomic nuclei. That is why NMR has been designated as 400 megahertz NMR, 500 megahertz NMR, etc. etc. How 400 megahertz NMR? You multiply by this magnetic field by fourfold. 2.35 into 4 is 9.4 Tesla. Again, you multiply this frequency by 4. The resonance frequency will keep on increasing that many fold. So the resonance frequency is directly proportional to the applied magnetic field, which in turn is proportional to the resolution. Better resolution is get at the higher and higher magnetic field strength. So under the influence of 9.4 Tesla, different nuclei precision frequency of oxygen 40 megahertz, carbon 100 megahertz, phosphorus 161 megahertz. Now we have put our sample inside the powerful magnetic field. Energy level has been created. It has been created by the application of external powerful magnetic field and stop to frequency. Resonance nuclear. In order to achieve resonance, we need one more frequency. Resonance means equal. What's the difference? We need one more frequency. What I am going to do, like in UV, we are going to irradiate the sample with the electromagnetic radio region of the electromagnetic radiation. So, and
So kindly unmute, sir.
Am I audible, madam?
Yes, sir. Now audible,
Thank
sir.
you. Yes, sir.
Okay. What about the
You have to
PowerPoint?
share your screen, sir.
Okay, you could see the PowerPoint PPT?
No, sir. No, sir.
Okay.
The
No.
presentation is not.
Now?
No, sir.
No?
Not yet it is presented.
No, sir.
So click on the share screen.
Saravanan?
Click on the share screen. The arrow.
Yeah, yes, I'll do it, madam.
Yes, yes.
Sharp. You sharp madam. இது share ஆகல. இல்ல, இது ஒண்ணும் இல்ல. நடுவுல disturbance இருக்கு. Right.
நெட்டே கட் ஆயிடுச்சுங்க சார். நெட்டு
Next.
லீவ் பண்ணி விட்டுருங்க. ஜூம் சரி அதான்
Saravana Kumar, sir.
சரி நான் ஜூம்
Saravana Kumar,
Share
sir.
பண்ணா போதும்.
Just share. You may close your presentation, current presentation, and reopen it again.
ஜூம் ஓப்பன் பண்ணுங்க.
Hello.
Hello, sir. Close the present presentation and share it
Okay.
again.
Okay. இது close பண்ணிடுங்க. Share it.
Yes, fine, sir.
Yes,
Okay, madam.
Yeah, yes.
Yeah. Yeah. Sorry for the disturbance.
No problem.
See, we have put the sample, or let us imagine a free hydrogen atom under the influence of external powerful magnetic field of 9.4 Tesla, precise at 400 megahertz. We are going to irradiate this sample with the electromagnetic radiation or radio frequency, radio region of the electromagnetic radiation, and tune the frequency to match to that of this resonance frequency 400 megahertz. When these two frequencies are equal, matches 400 megahertz, internal frequency, precision frequency is 400 megahertz, and the external radio frequency is also 400 megahertz. When these two frequencies matches equal, a resonance condition is achieved. The resonance condition is achieved. At the time of resonance, the nuclei in the lower energy level, or rather the excess nuclei in the lower energy level, absorbed the energy from the radio frequency or the electromagnetic radiation and flip to the higher energy. See, we are applying this energy in the form of a pulse. Pulse means what? We are applying it for a short duration of 10 microseconds, 15 microseconds, etc. Depends upon the type of nuclei which you are going to stimulate. So the moment you stop this energy, radio frequency, electromagnetic radiation, the nuclei or the excess nuclei naturally will relax back to the lower energy state, or rather what we call it as equilibrium, or to attain thermal equilibrium, normal state. During relaxation, while relaxing, it emits the excess energy which it absorbed during this process in the form of radiation. It dissipates to the surrounding. It dissipates to the surrounding. Let us see this diagram. See, this is our sample tube. The sample is inside, water molecule, whatever it may be. So we are applying to the coil. Coil means there is a copper wire is wound on this sample tube. Through this transmitter, we are applying the 400 megahertz radio frequency. And there is one more coil in green color. They call it as a wire. It's a receiver coil. They call it a receiver coil. So during relaxation, the excess nuclei dissipates the energy. So that the energy will produce or induces a current in the coil. That current has been plotted as NMR. So that is why this is the raw data. This is our NMR raw data. It is called FID, free induction decay or free induced decay. It decays on its own freely from higher energy to the lower energy state. It takes for about 1 second to relax. This time is called relaxation time, that varies from nuclei to nuclei, as well as depends on the type of nuclei environment the nuclei is there. So, but basically just note down one thing, but it's a time domain spectrum. That's a time domain spectrum. Time domain representation is of no use to us. We cannot interpret any results from this. So what is interested, what is our interest? X-axis in the frequency axis. We are interested in the frequency axis. Y-axis is the arbitrary or amount of it. It's not the percentage like in UV area. It is the amount of energy absorbed by the nucleus. So it will be converted using a mathematical technique called Fourier transform. That is why this NMR is called FT-NMR. Since we are using pulse to energize, we radiate the sample, this is also called pulsed NMR. So this is the practical actual NMR spectra will look like this. So this is the spectra, NMR spectra of some alcohol. This of alcohol. You could see 3 peaks here, 1, 2, 3. I thought I'll get only 1 peak. So putting alcohol inside the magnet, a powerful magnet, that's consumed alcohol and give rise to 2 peaks, it's drowsy. Is it so? We'll see the next slide. So far we discussed about only about the nuclei as a magnet. We never thought about the surrounding electron. Electrons surround the nuclei like a cloud. Where is this electron? It is everywhere. Like a cloud, it is there everywhere. It is a psi function. It's a negatively charged particle. So it produces the current, the negatively charged movement current produces its own magnetic field. So this magnetic field, it reinforces, sometimes it reinforces the external powerful magnetic field. This is the external field. And it produces its own magnetic field. Either it opposes the external magnetic field or sometimes reinforces also. It not only disturbs its own nuclei, it gives disturbance to the neighboring nuclei also. So, what is the meaning? This electron cloud shields our nucleus. This phenomena is called shielding. It's called shielding. Now again, to have a better understanding, imagine a free hydrogen atom. This is at 400 megahertz under the influence of 9.4 Tesla. But in practical situation, in a molecule, hydrogen with the chlorine, bromine, iodine, oxygen is bonded. Bonded means the electron only. So the bonding electron produces its own field, or rather, it modifies the electron density around the hydrogen atom. So a free hydrogen atom is without bonding, we can call it as highly shielded. Is in one different environment, or it's highly shielded, its density, electron density is the highest possible. Highly shielded or highest possible. The moment the electron is bonded to some nuclei, chlorine, bromine, because of the bonding electron, it produces its own magnetic field and creates their own magnetic field and modifies the external magnetic field. Hello, am I audible?
Yes, sir. Yes, sir. Audible, sir.
Okay. So what I want to say, this is the, imagine this is a free hydrogen atom. It is highly shielded. We need more magnetic field, for example, 9.4 Tesla to resonate at 400 megahertz. Since it is highly shielded, in a bond, it's de-shielded. As a result, we need less magnetic field to resonate at, less magnetic field is sufficient to resonate at 400 megahertz. As per the equation, if B is small, for example, instead of 9.4 Tesla, we may need 9.39 Tesla or 9.38 9.98 Tesla, 9.99 Tesla or 9.39 Tesla or 9.38 Tesla. Slightly lesser magnetic field is sufficient to resonate at 400 megahertz. So, what I want to say, there is a shift in the resonance frequency. The shift is due to environment. The shift is due to chemical environment. That is why it is called a chemical shift. A measure of the chemical shift. How many hertz it is apart from 400 megahertz. Tell us the environment of the hydrogen atomic nuclei. It is applicable to all nuclei. What is the environment of carbon, fluorine, nitrogen, etc. Now, let us take one example. In the case of water molecule, it resonates. Since it is proximity, hydrogen atom proximity to oxygen electronegative group, it's highly de-shielded and it resonates at a slightly lesser frequency, 399.998 megahertz. What I'm going to do, I'm going to plot this as NMR spectra. Using, I have taken NMR spectra of water molecule in my two spectrometers. I have two spectrometers. One is 400 megahertz NMR, another one is 500 megahertz. I have plotted this water molecule in my spectrometer. See the x-axis scale. So 400 megahertz, 399.99 megahertz, 399.98. The scale will go like this. In the case of 500, it spreads like this. So in one, the resonance frequency is 399.98. In another spectrometer, it is 499.998. There is no uniformity in the scaling x-axis. In order to bring uniformity in the x-axis, a new unit is introduced. That is what is called ppm, parts per million. How to derive the unit? What is the maximum in the case of 400 megahertz possible is 400 minus The actual resonance frequency of the water molecule is 399.98 divided by 400. This will give 4.7 ppm. This is called a del. They call it as some Greek word. 4.7 ppm. If we take 500 megahertz, maximum frequency is 500 minus the resonance frequency of water molecule is 499.998 divided by 500, it will give 4.1. If we take NMR spectra of water molecule, any NMR, 1000 including 1000 megahertz NMR, it will give a peak at 4.77 ppm. Now, how much spread chemical shift will be there? So in the case of hydrogen atomic nucleus, it will spread up to, in some cases up to 15 ppm. The spread is up to 15 ppm. So the one which is close to 0 ppm is called the high field or highly shielded region. The opposite side is called the low field or de-shielded region. Okay. So we need some reference. If we have free hydrogen atom, that we can use it as a highly shielded one. The molecule which is available, organic molecule, highly shielded molecule available with the TMS spectrometer theory, that frequency has been marked and labeled as 0 ppm. With respect to 0 ppm or with respect to TMS, how much should take there? So that is why we have chosen TMS, highly shielded one. And TMS we can use our standard or reference only for 1H and C13. For other nuclei, for example, P31, we have to use 88% phosphoric acid, and for chlorine we have to use THO. And if I remember correct, for silicon we can use even urea, etc. So different nuclei have its own standards. Now, what is the reason for shielding or de-shielding? One is the electronegative group and magnetic anisotropy, and third one is the hydrogen bonding. So electronegative group, you know, is a hydrogen electron withdrawal group. Now, as a result, if the symmetry is lost and produces de-shielding. One classic example, let us look at this molecule. CH3 is highly shielded, whereas in the case of CH2, because of proximity to the chlorine electronegative group, it gets de-shielded and it gives a peak in the high ppm picture and compared to CH3. High ppm. Let us take this example. There's see this difference: 1 chlorine, 2 chlorine, and 3 chlorine. This is highly de-shielded. Gives rise to peak around 7.27 ppm when compared to 1 chlorine proximity, 3 ppm. And again, magnetic anisotropy. Another example, the kind of classic example of the compounds like aromatic, alkene, alkynes, and carbonyl. So basic reason is the electronic structure. You all know quantum mechanics has assigned electrons in different orbitals: s orbital, p orbital, d orbital, and f orbital. Yes, in s orbital, it's in the symmetry, or what we can say spherical distribution of electrons, as shown in this figure. In the p orbital, it is not spherical distribution, it shows a number structure. The distribution is like this. In the d orbital and f orbital, it is like this. So, in the case of the classic example of aromatic compound, they produce a pi electron, pi bonding. The pi bonding is mainly due to the electrons in the 2p orbital. So the anisotropy, because of the dumbbell structure, the anisotropy is produced, and the non-spherical distribution of pi electron leads to the anisotropy, which in turn leads to the de-shielding. And the third one is the hydrogen bonding. Hydrogen bonding, you know, hydrogen bonding, what it does, it redistribution. It's not pulling the electron out, redistribute the electron density. So more the hydrogen bonding, more will be the redistribution, and more will be the shielding. And now we see look at some examples of the NHMO spectra. It spreads from 0 ppm up to 12 ppm. This is a general table only. What book says, in some books it is written 0 to 6.5 ppm aliphatic, HH to the all these regions, and 6.5 ppm up to 9 ppm aromatic region, aromatic compounds, 9 to 12 ppm here. aldehyde and the acid. The next slide is more elaborative. One censorship table is more elaborative, or different region, each and every region corresponding to different one. But if you do practically and do try to interpret the NMR from your work, you will understand much better. These are all centralized tables available in the website. Let us take one of the example. See, methyl. Methyl gives a peak around less than 1 ppm. Normally it gives a peak around 0.9 ppm. Methylene proton is around 1.2 and methane around 1.2. This is the general rule. This is the general rule. Just go to the next one. Now, how many proton environments are there? Or how many peaks will obtain? Or different environment the hydrogen atom is looking for. There are only two, we can say, two methyl groups are there. One is CH3 here and another one is CH3 here. And attached to this carbonyl group equally placed. We can call it as equal proton. We can say it there, equal protons. And what is the position of CH3? CH3 is supposed to give you a peak at a point below 1 ppm. Because of this proximity to this carbonyl group, it gives a peak well down to 2.2. Because of this proximity to this carbonyl group is de-shielded and gives rise to peak at 2.2. Next example, the equivalent and non-equivalent. CH3 it will give one signal, and CH this CH, because the environment is entirely different, and it will give a peak completely downfield. Downfield is more ppm. This is highly de-shielded. This CH is highly de-shielded and compared to this CH3. And here both A and B, this and this are magnetically equivalent, and these two hydrogens again magnetically equivalent. This will give you a strong intense peak, and these two protons will give you a strong, together will give you a strong intense peak. Here the symmetry is lost. Symmetry is lost due to the bromine substitution. As a result, all three hydrogens will give three differently, very close to each other, separated by a very few ppm. And again the benzene rings, all are equivalent, all are magnetically equivalent, and give rise to a strong intense peak at 7.28 ppm. Again, the symmetry is lost due to the substitution. Still, this ortho, meta, and para may resonate at the same frequency and give rise to 2 or 3 peaks. Depends. Next example, this is the chlorine, bromine, iodine electronegative group substitution. The CH2 supposed to give you a peak at 1.2 ppm. So due to its proximity to iodine, it go well down to 3.2 and 3.4 and 3.5 because of the proximity of chlorine, and down to 4.5 ppm because of this highly electronegative group. Right? These are all some of the simple and easy examples for our understanding. So now we will move on to the aromatic side. Benzene is a classic example. All 6 protons, all 6 hydrogen atoms, and all 6 carbon atoms resonate at the same frequency and gives a strong intense peak at 7.33 ppm. 7.33, exactly 7.33 ppm. This is one classic example. Next one. So the symmetry is lost. We have done substitution here. We have done a substitution, CH3 substitution here. The symmetry is lost. Symmetry is lost. So that we have got from the NMR spectra, what we can conclude, one peak corresponds to 0 ppm, corresponds to reference TMS, and the second, this peak corresponds to the this aliphatic. Third one is spread from above 7 ppm, 6.5 ppm. Probably it could be aromatic. And from this structure, all 5 hydrogen atoms may not resonate at the same frequency. Instead, the HA, HB, and HC. HA resonates at the same frequency, HB resonates at the same frequency, and HC resonates at the one frequency. We are supposed to get the 3 different peaks in the aromatic side. Right? One the aromatic peak for this all 5 hydrogen atoms, and one aliphatic for the CH3, and this is the TMS reference peak. Next one. Same substitution. Here, instead of the methyl group, the bromo substitution has been taken place. What is the difference between that spectra and this spectra? Because of this electronegative group, electron withdrawing group, the spectra, the aromatic spectra, will be shifted further down from 7.4 to 7.2 ppm. Previous case, it was between 7.2 to 7.4. In this case, the entire spectra has gone down to further down by 0.1 or 0.2 ppm because of this electronegative group substitution. This is one example whether to identify the compound is aromatic or not. The aromatic peak, as I told you, the general rule is from above 7 ppm, 7 to 9 ppm. It gives rise a peak at around 5.78 ppm. So the compound may not be, it's not aromatic, it's in the alkene region. This is one of the application of NMR to identify. See, from the NMR spectra, you could see there is a 6 is written here. 6 is there is a label, 6 is written here. What does that label mean? From the spectra, what are the other information we can derive? Derivable information. One is the chemical shift. From the chemical shift tells us the environment. The second information we can derive from the spectra, NMR spectra, one-dimensional NMR spectra is the integral value. What is integration? This is our NMR spectra. The area under the peak, the area, integrating the area under the peak gives us the quantification, quantitative information. Quantification means it's not like AAS or chromatography, weight per volume. It gives the information, the number of hydrogen atoms in a molecule. One information. Second information, the number of hydrogen atoms attached to the X nuclei. The X nuclei may be C, X nuclei may be N, X nuclei may be bromine, or X nuclei may be fluorine, any nuclei, X nuclei. So these two information we can get by integrating the area under the peak. Let us take this molecule. How many groups are there? 2, 3 plus 2, 5, 6, 7, 8, 8 plus 1. So total number of hydrogen atoms in this molecule is 9. Another information we can derive, since this is 2, probably it could be CH2. Since this is 3, here, probably it could be CH3. This could be NH or CH. Like that we can derive what could be the group. Let us see in the next example. This is a simple example of ethyl benzene, known molecule. And normally, integral label will appear at the bottom of this spectra, and the chemical shift appear on top of the spectra, NMR spectra. This is the molecule, and we have done on substitution. Substitution we have done. From the integration, we can conclude total number of hydrogen atoms is 3, 5 plus 2 plus 3, total 10 hydrogen atoms are there. Out of 5, 3 in the aliphatic, 5 in the aliphatic, and 5 in the aromatic region. And from this, we can conclude there could be CH2 and CH2. That is the first conclusion. And from the 5, we can conclude the benzene ring symmetry is lost, and that there is a substitution. Since we know the molecule, we can imagine immediately, we can conclude immediately. If it is unknown molecule, this is the way we can do. From the chemical shift and from the integral values, then we can conclude there is a substitution of CH2 and CH3. Next example, this is our synthesized compound. From the structure, how many peaks we can expect? One peak at the aliphatic region, CH2, one peak in the aliphatic region, and one corresponding to the aromatic side, right? Aromatic side, we expect one peak beyond 7 ppm. Up to 7 ppm, we can expect one more peak for CH2, one strong peak corresponding to CH2. But we have got 1, 2, 3. Additional 2 peaks are there. So this probably from the integral value, we could conclude probably this could be some impurities. So we should use only pure compound. Impurities is there. Impurity also, NMR doesn't know whether it's a pure compound or impure compound. Impurity also will give rise to peak. So we should ignore this peak and integral value. What is this? This is the solvent moisture peak. This we cannot avoid. So the solvent here is the CdCl3. If you open and close the NMR solvent bottle for a few times, 5 times or 6 times, then it will absorb moisture from there. That moisture also will give us the peak. Each and every solvent has its own moisture peak at different positions. If you use NMR solvent first time or second time, this peak won't appear. After subsequent time, so we have to ignore this peak and we have to ignore this peak. So we are left with only 2 integrals, this integral 1 and integral 2. But how many protons are there? Here 2 protons are there. Here 1, 2, 3, 4 protons are there. Total we should expect 6, but we have got only 3. So that's why we have chosen this example. Why I have chosen this example? This integral will not give directly the number of protons. We have to assign. We have to assign. How to assign it? We can multiply by this 2. You should know the starting material and the product. Or if any aldehyde is there, or any OH group is there, or any NH is there, that you can assign it as 1. Then with that 1 proton, we can assign the other proton. Or any methyl group with the CH3, that you can assign as 3. So that way only you can get the number of protons. So here we have to multiply this by 2. Then subsequently you will get this also will get multiplied. 4 plus 2, 6. So this point only I want to stress. Third thing, here this spectra. What is the difference between these 2 spectra? The same compound, alcohol. This has taken at the low resolution NMR. This has taken at the measured at using the high resolution NMR. There is a splitting in the pattern corresponding to CH3 group and CH2 group. There is no splitting observed in the OH group. So what it indicates, the first inference, there is a coupling between CH2 and CH3. First inference. It also indicates there is no coupling between CH2 and OH and CH3 and OH. This is an indirect. This first information, there is a coupling. So how coupling arises? What is coupling? What is coupling? How it arises? So this is our molecule. CH3, CH2, OH. This is a magnet. This is a magnet. See the proximity, vicinal. So there is an interaction between this to this, or to this to this. This interaction is magnetic interaction. If they are close, very close, less than 5 Armstrong unit or 5-6 Armstrong unit, then there may be an interaction. This kind of interaction is called through space interaction. Another kind of interaction or coupling, this they call it as this interaction, they call it as coupling. Spin coupling. Since this is a spin and this is a spin, they call it as coupling. This is through space coupling. And another coupling is through bond coupling. See, bond from one atom to another is through electron only. Electron is also produces this magnetic field. So this magnet influences the bonded electron, one bond. Again, it influences the bonded electron, second bond, and this bond. So it influences the here to bond, here, here, here. So it from here through bond electron, this hydrogen influences this hydrogen. This is magnetic interaction, through bond interaction, or this is called spin coupling. This is the way it is called spin coupling. This is one bond. How many bonds it can carry? 1 bond, 2 bond, maximum it can influence up to 3 bonds. So let us see a simple example, classic example. Let us take only CH-CH. Only two CH-CH groups are there. This is one magnet and this is another magnet. Both may be pointing upwards, plus Z direction. The another possibility, one may be pointing upward, this may be pointing upward, this may be pointing downwards. So both are influencing proximity to each other and they influence each other. If there is no coupling, If there is no coupling, we are now talking only about the through bond coupling, not through space coupling. If there is no coupling, this will give rise to a sharp peak up to 2000 hertz. Okay, now imagine there is a coupling. So the two possibilities are there. So it may give a peak at 1195 hertz also one peak will be there. 2005 hertz also will peak it. So this peak will split into doublet. One frequency corresponds to 1995, another one corresponds to 2005. They are separated by nearly 10 hertz. They are separated by nearly 10 hertz. Now, what is the rule? Is only produced that is called this is called singlet. This is called doublet. So the coupling will produce only doublet, but we saw in the case of ethanol one triplet also. What is the rule? N+1 rule. What the rule says, if CH is that this H will split this into doublet, this H will split this into doublet. If CH3, CH2 is there, this H will split this into doublet. This CH2 is there, this will split this CH into triplet, like this. And the CH2 and CH3, the CH2, two protons are there, this will split the CH3 into triplet. The CH3 in turn, three protons are there, split the CH2 into quadrat 4. So on what intensity will be there? Doublet will be in the intensity, equal intensity, triplet in the intensity 1:2:1 intensity, and the quadrat in the intensity 1:3:3:1 intensity. So what is this use of this coupling? This is designated by the subscript J. 1J means one bond coupling. 2J means two bond coupling. 3J means three bond coupling. And long range coupling will also be there. So it is designated the unit of coupling constant is expressed in terms of jargon, NMR term is called J. How many hertz? J in hertz only. Because the exact is the hertz only. How many hertz they are separated, doublet, triplet, etc. What is the information we can derive from this? Very vital value, very useful information, valuable information we can get it from the coupling constant. They are expressed in, so normally proton-proton coupling spread up to maximum of 14 hertz. What is the information? Geminal, whether it is a geminal or it is a vicinal, whether the compound is a cis or it's a trans or it's a long range or it is an isomer. It gives information about all this information, minimum information I'm telling. We can derive many information from the coupling constant. And it is very useful for the three-dimensional structural elucidation of the knowledge. This is all about this. So here, this proton and this hydrogen atom is one bond, two bond, and three bond. So maximum it can, this magnet will influence this magnet, maximum up to through bond, maximum up to three bond. There may be coupling. Here, one bond, two bond, three bond, four bond. There may not be any coupling. Here again, it is one bond, two bond, three bond, four bond. But there is a double bond is there. There is a double bond is there. There may be, may or may not be a coupling between HA and HB. Now let us see the simple example. There is a, see the splitting itself speak. There is a coupling between CH3 and CH. See this, see the integration. It is in the ratio of 1:3. See itself speak. This is CH3 and this will speak CH2. Why it comes down to very close to 6 ppm because of this. Not only one chlorine is proximity to 2 chlorine. That's why it has come down very close to 6 ppm. This is another example. CH3 seems to be a bromine proximity. So this splits into triplet, in terms it splits into triplet and 13C NMR. So far we discussed about the proton NMR. What is the difference between the hydrogen NMR and 13C NMR? One is the abundance. Hydrogen abundance is 100%. Whereas 13C abundance is only 1%. Means 12C is 99%, 12C in atom. And if we take 100 molecules, 12C is 99% and 13C is 1%. So we need more samples for about minimum of 20 milligram sample to do NMR measurement. It takes long time for about minimum half an hour to 1 hour. These are the disadvantages of 13C NMR. And another thing, the spectral width is spread up to 230 ppm. This is another information. And whether we get any splitting in this, because splitting will take place only one magnet is in the decimal of close to another magnet. In 13C, the natural abundance is only 1%. So on 13C, cannot see the another 13C. It will be far away. So there won't be any splitting. There won't be any integration also. These are the information from the 13C NMR. Again, this is the general table, like in proton NMR, 0 to 100, 110 ppm corresponds to all aliphatic, whatever aliphatic groups are there. 100 to 160, 170 ppm is the aromatic region. 170 to 180 ester, amide, acid. Then comes the aldehyde and the ketone groups beyond 200 ppm also. This table is available in the website. Without this table, you cannot interpret it in the initial stages. And let us take one simple one or two examples. How many 13C signals or 13C groups are there? See, obviously CH3 group. See, many CH2s are there, but because the CH2 is attached to this oxygen group, because of this oxygen proximity, it will go well down. So this CH2, this 60 ppm corresponds to this CH2. And CH3 obviously will be very close to the 0 ppm. This is CH3. And this CH2, we have to assign this way only, this CH2 and this CH2. This way only we have to assign. Next one. Again, one more example, good example. Two methyl groups are there. But this methyl group, because of this proximity to the carbonyl, it is downfield. See, first PMS, very close to the reference, this methyl group, and next this methyl group, and the CH2, because of this proximity, it is also down to 40 ppm. And the carbonyl group is obviously, like in the previous table, is around close to 200 ppm, close to 200 ppm, 200 or more than that. Sometimes it may even go down to 220 ppm. It depends upon the type of environment. And one aromatic compound, all like hydrogen, all resonates at the same frequency, gives a strong intense peak at 128 ppm. Here the symmetry is lost. So because of this bromine substitution, the symmetry is lost. Still we can expect 1,1 carbon resonates at the same frequency, 2,2 carbon, this carbon resonates at the same frequency, this carbon resonates at the same frequency. Because of this proximity, the carbon at one position will be slightly shifted down. Again, this 2 and this 3 and this. Okay. And now one more important experiment in the case of depth. We have CH, CH3 and CH2 all different kinds of carbon. How to differentiate that? Important experiment is called distortionless enhancement polarization transfer. And let us see one example. So there are experiments only. There are selected experiments, standard experiments. This is the normal C13 experiment of this compound. It gives CH, CH2, CH3, quaternion carbon, and all carbonyl group, everything, all esters and all. If you do depth 45, it will give only CH, CH2, and CH3. It gives CH, CH2, and CH3. Depth 90, it will give only CH. Depth 135 will give CH and CH3 positive and CH2 negative. It means these are all CH2s. These are all CH2s. Comparing this and this is CH because depth 90 will give only CH. And this will give CH and CH. This is CH3, this is CH, these are all CH2. Right? This is one more important experiment. This is one-dimensional NMR of protein molecule. So can we do any interpretation for this? There is overlapping of peaks. Then we have to go for one different technique called two-dimensional NMR spectroscopy. That is what is called a correlation. That gives the correlation between different groups. There are two types of correlation. One is homocorrelation, another one is heterocorrelation. Homocorrelation means between proton-proton and C13, C13, 19F, 19F. Heterocorrelation means between proton and C13, proton and 19F, proton and 15F. Different kinds of correlation. These are all standard experiments, what is called COSI and total correlation. Here they call it as NOSI and ROSI. So this NO-C and Rho-C are mainly meant for through space coupling, mainly meant for through space coupling up to 5 Armstrong units. This correlation, CO-C and 2-CO-C, is mainly meant for through bond coupling, spin field coupling through bond coupling. That is the difference between these two correlation experiments. This is the different kinds of heterocorrelation. Heteronuclear single quantum coherence, heteronuclear multiple quantum coherence. These two are meant for only one bond, CH1. This is heteronuclear multiple bond, more than 3 bonds, HMBC or even HMBC. You should know your molecule, how many bonds correlation you need to measure. This is one example of the heteronuclear correlation. NH sequencing. And what are the applications of NMR? We can do in situ electrochemical measurement using 3 electrode, working electrode, counter electrode, reference electrode inside the 5 mm tube, and do live in situ electrochemical oxidation and reduction reaction. Time and temperature result. Temperature means -100 to +100. There are positions inside the NMR spectrometers of that. Time, variable time. Every 5 minutes, every 10 minutes, or 15 minutes, you can monitor the reaction. The T1 T2 relaxation. It tells that the environment varies, then the T1 T2 relaxation time also will give that very valuable information. And high pressure NMR. See, there are special tubes are there, NMR tube 5 mm NMR tubes are there, where you can pressurize the sample up to 20 bar, 30 bar. It gives information about the NMR dynamic. The water separation is mainly meant for the NMR solvent. You can use water or D2O. And you can do kinetic studies also. We can measure diffusion coefficient measurement. The correlation time, tau C, you can measure it. And molecular dynamics using T1 relaxation and T2 relaxation we can do. NMR studies are one of the only one application. This is our work we did it. NMR studies on the composition of PVD HFP membrane on the lithium battery. So we have taken this membrane and in 3 different concentrations. So 10% polymer means 10% polymer content with 90% of the plasticization. And 20% means 20:80 and 30:70. And we measured 7 Li NMR at different temperatures, and it has been plotted. This is 10% polymer content, this is 20% and 30%. And from the spectra itself, speak about the charge carrier movement. So in the case of 10%, enough charge carriers are there because only 10% polymer is there. In the case of 30, more charge carriers are there. Whereas in the case of 20%, enough charge carrier or sufficient charge carriers. Charge carriers means basically lithium ion charge carrier. Basically it means for conductive lithium ion conductivity. We measured indirectly the conductivity of the lithium ion charge carriers in the PPTFHFP membrane. This is one of our work. We did some coordination reaction at a variable temperature and time measurement. And this is we synthesized on compound aerobium magnetite, bulk and nano. In the case of nano, it gives a very broad NMR peak. So we concluded that the oxygen deficiency sample obtained in the case of method, sample preparation method, Sargent method, needs to be broad separation. It means it relaxes much faster. That was the conclusion. And this is the diffusion coefficient measurements. We did it. One of the water separation experiment. This is without water separation. The water peak is very dominant. Once you suppress this, the other peaks are genuine peaks appear well. And this is some of the uses of the NMR. And these are all some of the applications of NMR. Now, sample preparation. Sample preparation. This is the NMR standard NMR tube. How to prepare the sample? We have to measure. There are solvents. NMR grade solvent. NMR grade means nothing but deuterated solvent. We have to use, instead of CHCl3, we have to use CdCl3. That is the meaning. It's a bit costlier. And we have to use only deuterated solvents. So we measure the sample. 5 to 10 milligram sample in the case of 1H NMR is needed. And we measure it using a balance. And remove any solid particles. And take for about 0.5 ml of solvent, deuterated solvent. And label it, sonicate it, degas it, and see the solubility. It should be highly soluble, and you can even using filter paper you can filter it, and transfer it into the NMR tube. This is the NMR tube. This they call it as a spinner or sample holder. We can call it as a sample NMR sample holder that has been kept inside the. This is the auto sampler. We can load 24 samples, 1, 2, 3, after labeling it. And this is the probe. This is the NMR probe. Sample will go inside and will sit inside the probe. This is the sensing coil. It senses the NMR signal. This is the NMR. The sample is loaded here in the auto sampler. This will go here automatically and will go inside the magnet. There are standard programs. If you want to do 1H, you have to select 1H. If you want to do 13 NMR or 15 NMR, 31 NMR, you have to select programs. And if you want to do 2D NMR, division coefficient, automatically you can select it. It will run it. Before that, there are some small procedures are there, like insert the sample into the magnet. Then perform tuning and matching, because each and every nuclei has its own resonance frequency. We have to tune the frequency and match with that of the frequency. Shimming, because the magnetic field on all sides of the NMR tube, it won't receive a uniform magnetic field. In order to make the magnetic field, we have provided some shim coil. As well as what we do, we spin the sample at 20 Hertz. We cheat the magnetic field. While spinning, the magnetic field gets averaged out. That's the two things. We spin the sample at 20 Hertz and we do perform shimming, and we log the sample. Why we log the sample? Two problems with the magnet. One is the magnetic field won't be stable. There may be a small variation in the magnetic field. There are many reasons. Main thing is the temperature variation. And if there is any drift in the magnetic field, CHD group 1.9 ppm should appear. Will produce a peak at 1.2 ppm. There will be a shift. So the deuterium will always act as a watchdog and use the correctance factor. That is what is called field frequency log. That is what is called the field. That's why we use deuterator. One purpose of using deuterium is that your solvent will give you a very strong peak. Chloroform, water will give you a very strong peak. If you use deuterium, NMR will not sense deuterium. It will sense only 1 H, not 2 H. So, to make your peak, your genuine peak or sample peak, better than this solvent peak, we use the deuterator. So, the deuterium, we use deuterated sample we use for these two purposes. One is for field frequency log, another for getting the genuine peak of our sample. Perform receiver gain optimum. See, if the sample concentration is very less, we have to go for a higher gain, like amplifier, volume, increasing the volume in a amplifier, and start the experiment. Which experiment you want to do? 1H, C30, choose the experiment. And while applying the data, raw data, you have to process it. What is the processing? There are steps are there, and you can choose the chemical shift. You can choose your integral values. These are the things you have to do. What is meant by processing the data? You can avoid unwanted peaks by integration or by doing some mathematical formula. You can avoid some other things also. And this is the solid state NMR. The problem with the solid state NMR, in the solution state, it gets averaged out. One magnet is all basically a magnet. One magnet cannot see another magnet due to Brownian motion. But it's not the case in the solid. It's very close to each other. So the one magnet will influence the other magnet. That is what is called anisotropy. So the solid NMR spectra, it will look like this. What we do, we spin the sample to average out the this magnetic anisotropy, and the solid NMR spectra will look like this. These are called spinning cycles. We spin the sample at 10,000 RPM, 15,000 and 20,000 RPM. So, and they try to average out at some angle. That angle is called a magic angle. That is why the solid state NMR probe is called a MAS probe, magic angle spinning at 54.52 degrees with respect to Z axis. And this is about the instrumentation. Basically, I told you there is a superconducting magnet. What is superconductivity? We can basically inside there is a coil, copper coil, aluminum coil. That is their trademark. The company's trademark. The magnet itself, superconducting magnet itself, costing around 3 crore rupees. So that is the trade secret. That is their 50 years work. Thousands of technocrats, scientists, engineers work, and they come out with this product. They call it as niobium titanium coil. I see if you heat any metal, the resistance will increase. If you cool it, the resistance will go down. So what they have done, this niobium titanium wire coil has been immersed in liquid helium temperature. Liquid helium temperature is nearly 4 degrees. So the resistance is almost nil or almost negligible. If you pass current to the coil while installation for about 100 ampere current and not the two ends of the coil and put it inside, there are provisions of that. They have manufactured it in such a way. They send the magnet from the Germany and they pass the current here. And they not these two ends of this magnet, the same transition, they pass the current through this, and finally once the resonance is such a resonance condition is, they close this two coil, it is closed. So it is like a permanent magnet, it is like a electromagnet. This is also called superconducting magnet because this attained superconducting, there is no resistance for the flow of electrons. So this is also called superconducting magnet. So it's immersed in liquid helium. Liquid helium, helium is very precious. We are getting liquid helium from Dubai by ship. 1 liter costing around 2,000 rupees. Yeah, if they keep on evaporating it, keep 1 liter liquid helium in no time, it will evaporate. To minimize the rate of evaporation, it has been kept in different jackets, like a flask. So outer jacket, helium outer jacket is filled with liquid nitrogen. Again outer jacket is evaporated. Again outer jacket filled with liquid nitrogen. It's like a different flask. Basically it is kept in liquid nitrogen, liquid helium temperature. So this is probe, the sensing element. The probe is costing around 40 to 50 lakhs. Many types of probes are available for solid sample, liquid sample, microscopy, cryoprobe, diffusion measurement, high temperature, low temperature, etc. There are hundreds of probes for various applications are available, various applications. And what are the samples? Everything, there is no restriction. That is the beauty of NMR. So we measured from organic division diced cloth. We cut the cloth and put it. The fine powder and wire, we put it inside the solid, filled with some silicon powder and measured it. Pellet. And we cut the thin film and we measured it. So everything is there. Sample indicated this NMR. That is the beauty, that is the advantage. It finds application in almost all fields. So how you use the tool? It's a tool. How you use the tool for your need. And some of the references paper, there are many references available in the website. Some of this book is a very good book by Neil Jacobson. It's a very good book, you can follow it. There are 200 more NMR experiments. Once you have the machine, then you can buy this book. And thank you. And thank you for the patience. So I have consumed a lot of time of Saravana Kumar.
Sir, sharing your valuable knowledge with us. This
Okay.
session is really informative. Having few questions from side. And one by one, sir. Will you please? We are having few questions from participant side, sir.
Yes, madam, please.
Okay, sir. So the questions are shown in the slides.
First question is from Selva Kumar. When the magnetic field is applied, how the two energy levels are created for hydrogen atom?
So it is not only for hydrogen atom, it is the atomic energy level. See, as per quantum mechanics, energy levels are quantized. See, for electron, energy levels are quantized in orbital, s orbital, p orbital, d orbital. Like atomic energy levels are also quantized. Quantum mechanics has assigned certain energy levels under the influence of external magnetic field. In the case of magnetic resonance, it is the magnetic energy, atomic nuclei magnetic energy levels are quantized, restricted energy levels, discrete energy levels are quantized by the quantum mechanics, by the application of external magnetics. It's quantum mechanics. Basically, it is a quantum mechanics.
Thank you, sir. The second question is from Preeti Sharon. Is there any software for NMR spectroscopy?
Yes, sir. what you can do, we go to website, type
And
Bruker,
okay, sir.
free NMR software. Type
Okay.
Bruker, free NMR software. It's available freely. And I think there are two main competitors. One is Bruker from Germany. Another company is Geo, Jeol from Japan. Jeol from Japan. Their software is also freely available. Their software is also freely available. It is available freely in the website. If you load this the raw data, you can process and you can learn it also. NMR software, you can learn it also.
Okay, sir. Thank you, sir. I think the next question also she raised. I hope she got the answer for this. How to interpret the NMR spectroscopy result? Now she got the answer. I think so, sir. So I move on to the next question. Kindly suggest the delta values of primary amine hydrogen, secondary amine hydrogen, hydroxy hydrogen.
So, if website you visit, there are tables are available. As I told you, the chemical shift tables. That is our reference only. That you can take it as a reference. Moreover, this value vary from molecule to molecule, experiment to experiment. The environment changes. So that you should know your molecule is your baby. You should know your baby. You can judge better. Simply, I can tell it may come in this ppm, 5 ppm, 6 ppm, like that. But if you want to go to precise value, you have to refer the table, chemical shift tables.
Okay, sir. The next question is from Thirumagal. Is it possible to take NMR for green synthesized metal nanoparticles?
Yes, only restriction, you should not be a magnetic material. Nanoparticle generally gives rise to a broad NMR signal, like in XRD, broad NMR signal.
Okay, thank you, sir. The next question is more about the integral value. What are we counting to get the value?
I told you number of hydrogen atoms in a molecule, one thing. And how many hydrogen atoms attached to the X nuclei? X nuclei may be carbon, fluorine, nitrogen, maybe anything, right? CH, CH2, HF, maybe anything. Number of hydrogen atoms attached to the X nuclei and total number of hydrogen atoms. That is this through information only we can derive from the integral.
Okay, sir. Thank you, sir. Next question is from Ram Kumar. So, ROSI NMR spectra applications. He is asking about
As I
ROSI.
told you, coupling only.
Okay, sir. The next
Distinction
question is
coupling, there are two types of coupling, as I told you. One is the through bond coupling, another one is through space coupling. Through space coupling, you can get it from NOC and ROSI. NOC experiment and ROSI experiment. The difference between the NOC and ROSI, if I remember correct, again, ROSI meant for moderate or up to 500 Dalton to more than 500 Dalton. NOC is restricted up to 1000 Dalton, if I remember it, that you can refer. This is the difference. It's mainly meant for through space work.
Thank you, sir. Next question is from Anish. Sir, C13 and C12 has only one neutron and is different. Based on this difference, C13 is NMR active, but neutron is chargeless species. But how this affect by the effect of external magnetic field. Based on electromagnetic theory, charged particles only can create magnetic field during their acceleration. But here, chargeless neutron having spin half value, how will create or get influenced by external magnetic field?
What is 0? 1 minus 1 equal to 0, right? You put one positive charge, one negative charge. So neutral means there is the two charges inside. One plus charge is there, one minus charge is there, right? So it becomes neutral. That way it produces its own magnetic field. That's the answer.
Sir, one more question in the chat box. I shall read it, sir. What technique of NMR is commonly used for herbal products that contain multiple constituents in a sample?
The main thing is, as I told you, one-dimensional NMR, and two-dimensional NMR spectroscopy. One-dimensional simple organic molecules and two-dimensional if we go for heavy molecular weight like protein, peptide, amino acids, it cannot be proved using one-dimensional NMR. As I told you, I showed on one-dimensional NMR spectra of protein, overlapping of peaks. So whether how many peaks are there, a maximum up to 10 peaks are there, then one-dimensional NMR spectroscopy, simple 1H and C13 is enough. In the worst case, we can go for one depth, 135, depth 90 and 45 is enough for it. No need to go for any two-dimensional. If it's a complex molecule, it's a complex structure and all, then you have to go for OC and even one heteronuclear, one homonuclear correlation and one or two heteronuclear correlation is a must. Is a must. It depends upon your type of sample and molecule complexity.
The
So
last
you have
question.
yeah.
So last question from Dr. P. Karpagam. Do 13C NMR SIPs of an organometallic compound obtained from solution and from the solid vary significantly?
The organometallic will give rise to peak minus peak, minus side, 0 to minus ppm. Organometallic will give rise to peak. As I told you, the electron either opposes or reinforces. When it opposes, then it will go to the D shielded and go to the higher ppm side. So when it reinforces, then if added up to the field, for example, 9.4 Tesla means 9.4 on Tesla, then it will go to the minus field. Organometallic, especially gives from 0 to minus 50.
Thank you, sir. Thank you very much for your wonderful delivery of this session, sir. I hope all the participants are now thorough in NMR. You made the NMR spectroscopy as a very simple one, not only instrumentation, the theory background, everything, sir. Thank you very much, sir.
I hope all the participants must have enjoyed my lecture. How far I could reach them or satisfy them, I do not know. Because I understand it's a mixture of UG, PG, and researchers. Everyone has their own demand. I tried my level best. In the next session, we'll go further with some research work to satisfy some other group of people. I once again thank management, American College, and particularly Madam Nazira Pone and Madam Jhansi Rani and this faculty of Central Instrumentation Center for the opportunity. We'll meet in the next session. Thank you. Thank you, sir. Thank you. Thank you for the
Thank
questions.
you, sir.
Thank you, sir. Thank you very much, sir.
Okay, okay.
Jemima ma'am, shall we move to the next session?
Yes, Pa. You can start the introduction of the next speaker and
Okay, ma'am. Okay, ma'am. Good morning to all. It is indeed a great pleasure for me to take this opportunity to introduce our chief guest of the second session, Mr. Saravanan, MSc, MPhil, Diploma in Industrial Safety, PGDCA. Right now, he is serving as a technical officer in CSIR Secretary, Karakudi. He is an approved technical person for Food and Drug Administration by Government of Maharashtra, NABL assessor and ISO IEC, trained GLP analyst in pharmaceutical formulation preparation and testing. He is one of the members of Quality Control Council of India. He is also a lifetime member in Chromatographic Society of India. Moreover, he has had a professional analytic and testing experience for 15 years in companies like MJ Laboratory Private Limited, Mumbai, Rajasthan Drugs and Pharmaceuticals Limited, Jaipur, CSIR CDRI, Lucknow. Besides, he is also known for his expertise in areas like raw material and API analyst in GLP formulation, drug standardization and quality control analysis, analysis of herbals, chemicals, finished products and intermediates of drugs, experience with IP, BP, USP and EP and other international pharmacopoeia analysis, analytical support to TGC 1 CDCSO, analytical method development and validation, calibration, maintenance, and troubleshooting of laboratory instruments like HPLC, UPLC, and HPTLC, and UV visible spectroscopies. Now this session is over to Mr. V. Saravanakumar. Sir, may I call upon you take us through the rest of this webinar. Welcome you, sir. Now the floor is yours. Hello, sir.
Just wait for him.
Oh, sir, unmute your speaker.
Please unmute you.
It's fine, sir.
Thank you. Shall I start?
Yes, sir, please start. We have introduced you to the audience.
Myself, I have to introduce.
Yeah.
Okay.
No, sir, be introduced yourself.
Thank you very much. Okay. And good morning to all my dear friends, and colleagues, faculties, and industries members. Okay. So I'm very happy to share my experience with you all. So I will sincere and special thank to American College, especially principal and convener and co-convener. Okay. All of my dear students. Okay. I would like to thank to you all this wonderful opportunities which was given to us. Okay. So I think last session you are all enjoyed. Okay. Now you are going to enjoy one more session, atomic observation spectroscopy. Okay. So let us move for the slides. Madam?
Any help,
Hello?
sir? Oh, sir.
Ji, madam. Actually, I cannot be able to share these slides with you. I think I got a message from post disabled participants screen sharing. Kindly check it out, madam.
Okay, sir.
Make him co-host.
Yeah, yes. Just now, sir. Sir, now you can start.
Yeah, we are getting you.
Okay, thank you, madam. Okay. Myself, I am Saravanakumar. I have completed my PG and philosophy. Now I am pursuing PhD. Okay, so I am one of the enable assessor. That means auditor in drugs and pharmaceutical, and a GLP trained analyst also. And I am one of the approved chemist for the Food and Drug Administration of Mumbai for the analytical, wet chemical and instrumentation, and one of the full member in Quality Council of India, especially in Chromatography Society of India. Now I am working as a technical officer in SECRE in the division of Central Instrumentation Facility Division. Okay, I have the 15 years experience in the research experience in the field of chromatography and thermal spectroscopy, especially in atomic absorption spectroscopy. Okay, madam. So, my dear friends, so today I am very pleasure to share my experience, what I have observed in my past life through the atomic absorption spectroscopy. Now I am going to share with you all. See, okay, so first I will start with my slide from the discoverer, inventor. Okay, so any instrument, any kind of instruments, before starting the instrument, okay, we should know that who is the inventor and when it was invented or discovered and which place. This is very important for us. Okay, so we have to thank to the particular personalities which was given to us currently in our hand. So everybody from today onwards, you can go and start your behavior yourself. That means any kind of instrument you are, before entering the instrument facility, otherwise instrumentation, before going to utilize, you should know that what is the basic fundamental and what is the, who is the inventor and discoverer. Okay, and according to that, atomic absorption spectroscopy is developed by the Sir Alan Walsh. He is a British Australian physicist. Okay, in the period of 1950 at Commonwealth Scientific Industrial Research Organization at Melbourne, Australia. Okay, so this is a brief hint of the instrument. Okay, okay. Now I am going to start with atomic absorption spectroscopy from the basic. So before going to the instrument, we should know the few of the points, and we have to remember the few of the points. First thing, instrument where we are using. So according to that application, we make the aware of the instrument, how much it is possible, how much is important in our lifestyle. Okay, according to that, atomic absorption spectroscopy used for the, especially for the elemental analysis of water, drugs, pharmaceutical, agriculture, food and cosmetics, and etc. Okay, this is a very important application for AIS. Okay, then next, this is mainly deals with the absorption and the emission of the radiation by atom. Deals with free atoms, and we can find so we can use for both qualitative and quantitative analysis. Okay, this is a few hints before starting to the AIS, atomic absorption spectroscopy. So these few of the points we have to remember once again. Okay, so atomic absorption spectroscopy generally based on that Beer-Lambert's law, atomic absorption spectroscopy mechanism is based on the Beer-Lambert's law mainly, and fundamental chemistry. Fundamental chemistry means, I think you are all studied alpha principle, Pauli's exclusion principle, and quantum numbers, primary, secondary, angular momentum, and spin. In that, you are studied SPDF, KLMN, number of electron filled to 6, 10, 14, respectively, of SPDF, and spin plus or minus. Okay, these are all the quantum chemistry which was involved in the atomic absorption spectroscopy. Okay, these are very basic. We are all studied. We are all now well known about these all fundamentals. from plus 1, plus 2, and UG, PG. Every time, everywhere we are studying. But we don't know where we are using and where we are applying that. Okay? For chemists, for physicists, those who are working in that atomic absorption spectroscopy, so we have to remember once again, that means all the things we are studying, but we don't know where we are using that. Okay, today I am going to correlate where we are studying and how we are using that. Okay, once again I remember you that Pauli's exclusion principle and alpha principle and quantum numbers and Beer-Lambert's law, these are all mixedly involved in the atomic absorption spectroscopy. Okay friends, we will go for the next. Okay, before going to the study about the atom or element, so our Bible of the chemist is periodic table. So periodic table is our holy book. So every chemistry beginning with periodic table only. Every branch of chemistry based on the periodic table only. Okay, this is our holy book for us. Okay, so from that periodic table, I think we are all aware all the elements. Okay, so what is the metals, what is the non-metals, what is the metallites, what is the radioactive, what are the elements is there, what is the liquid metals, okay, which one is the precious metals. Okay, so again we have to remember once again about the metals and non-metals and metallites. Okay, so periodic table further classified into 3 types: metals, non-metals, and metalloids. Okay, again I am repeating, periodic table further classified into 3 types: metal, non-metals, and metalloids. What is the meaning of the metalloids? Metalloids means this was having the behavior of both metals and non-metals sometimes. Okay, and so atomic absorption spectroscopy is used to detect metals and metalloids. Around 60 to 70 elements we can analyze. Okay, radioactive element not performing. We are not analyzing radioactive elements and inert gases and non-metals. Okay, and cationic properties and solubility is an important role in the atomic absorption spectroscope. Okay, these are all which was detected in that pink. So the pink color box, that means we can be able to analyze through the atomic absorption spectroscope. See, okay. Okay, in that periodic table, we should know that importance of the metal, our day-to-day life. So, ICH guidelines, I say International Council for Harmonization of the Technical Requirements for the Registration of the Pharmaceuticals for the Human Use. They are recommended guidelines. Okay, means they are classified into 4 types of the metals. Okay, for the safety purpose. One is a class 1, another one is a class 2A, another one is a class 2B, and final one is a class 3. Okay, class 1 is very, very dangerous for us. We have to limit it in our day-to-day life, like water and food and etc. Arsenic, cadmium, mercury, and lead is a very, very important and very toxic metal also, and followed by cobalt, nickel, and vanadium, and then ruthenium, rhodium, palladium, gold, silver, iridium, osmium, palladium, selenium, tellurium. Okay, lost lithium, barium, molybdenum, chromium, copper, tin, and lead, tin and antimony. Sorry. So this is the typical instrument which was placed in our central instrumentation facility at Secretary Karaikudi. So we are using that thermo product IC3000 series. So this is the typical model this is the atomic absorption spectroscopy flame, based on the flame. This is based on the graphite furnace. Okay, this is the auto sampler. Okay, this is the exhaust. Solar software we are using in our facility. Solar software we are using that. Our model is ICE 3000 series. Okay, the explanation, the definition, and basic and everything is same and common for all the instruments. Okay, this is scheme diagram of the AAS. Scheme diagram of the AAS. You can carefully, you can see and watch the diagram. See, this is the cathode cathode lamp. This is the burner. This is atomic absorption slit, monochromator, detector, and mixing chamber like nebulizer, sample input, and fuel gas and oxidizing gas input, means flame gas. Okay, fuel gas is input. Okay, this is the typical scheme diagram of the AAS. Cathode cathode lamp. This is the flame. Here we are going to analyze what is the concentration of the element present in that inserted solution. Okay. Then after the cathode cathode lamp, it was passing through the flame and detecting the concentration of the element which was already present in that your solution. Okay. And cathode cathode lamp is, we are selecting respectively which element we are going to analyze. For example, suppose we are analyzing sodium, we are analyzing silver, we are analyzing that iron. So you can go and select a selective lamp, means cathode cathode lamp of iron, cathode cathode lamp of sodium, and cathode cathode lamp of silver. Okay. Individual element having individual lamp. This is the final. Okay, so now AS classified into two types. One is a flame atomic absorption spectroscopy, another one is a graphite furnace atomic absorption spectroscopy. Okay. Okay, this is the flame atomic absorption spectroscopy. Okay. So this again I was showing the typical model, that same. Okay. For your remember purpose, the continuous slide is going on. Okay. So you will not get the remember once again. Okay, that's why every slide I am putting the schematic diagram for your understanding purpose. Okay, so I will go through that one by one. When solution of metal ions are introduced into the flame, in several processes occur in extremely rapid process. Means solution of metals are introduced into the flame. That is solution of metal ions, that means test solution introduced into the flame. With several processes occur in the extremely rapid process. That several processes occur in the nebulizer only. Then step means several processes occur extremely in the rapid process in nebulizer only. The first step is first solvent evaporates, leaving behind the formula units like NaCl, AgNO3 of the formally dissolved salt. Means, for example, you can consider NaCl or AgNO3 dissolved in that test solution. First, in that test solution, we are dissolved with that water. That means water will first evaporate. That is the meaning that first solvent evaporate, leaving behind the formula units. Next, dissociation of the formula units of salt into the atoms and ionized atomize are transferred into the atoms. Okay, occurs. Dissociation of the formula units, that means is converted into the ions under atomization or transferred into the atoms. If the atoms are easily raised to the excited state by the thermal energy, then flame, the resonant process occur in the atoms resonate and between the ground state and the excited state. That means, I will explain you. Dissociation of the formula in salt into the atoms occurs. Most of the ions atomized are transferred into the atoms. That means we are introducing into the flame, and due to the flame, only 0.1% of that atoms will excited from the ground state to excited state. So again, I am very interested to explain the ground state, excited state. We are studying that always ground state, excited state. We are writing, we are understanding through the two parallel lines only. Ground means bottom and exit means top. What is ground line? What is the upper line? That is nothing but ground and upper line. So I will show you the slide. Ground means K, excitement L में, excited में M or N, means K to L or L to M or M to N. It may vary. See, ground state means you can consider means that means next level of the means, for example, suppose atom having the electrons up to N cell, okay, that means N is a ground level. Means next stage is K, L, M, N, O level. Okay, for example, suppose we are having that electrons till M shell. That means M is ground state and N is excited state. See, for absorption purpose, the incoming photon is absorbed by the atom and excited. See the level K and L. K, L and M. This is the thing. So we should understand, we should first understand what is the ground level, what is the excited level, what is the okay. So what is the now we are, I think we are understanding that what is the ground state and what is the excited state. Okay. When the solution of metal ions are introduced into the flame, in several processes occur rapidly, the first solvent evaporates and molecule will get the break into ions. This is the thing, first step. Actually, only small percentage of the atom, less than 0.1%, depend on the temperature flame, are found in the excited state. Suppose we are introducing the solution into the flame, the only 0.1 or less than the 0.1 of the atoms only excited to the ground, excited to ground to excited state. Okay. As these atoms drop back to ground state, whatever atoms electrons are excited, that will back drop to the ground state. That is the emission. That is a spectrum is emission spectrum. Okay. For those atoms that are easily excited under these conditions, the emitted wavelength are the visible region of the spectrum. The entire flame on account the characteristics of the element in the flame. Okay. So some of the only 0.1 and less than 0.1% of the atoms only excited through the thermal energy like flame, that after the excitation again it was getting dropped down to ground state. This spectrum is called as the emission spectrum. Now we are discussing how much energy is required to promote ground to excited state of the remaining 99% of the atoms. Remaining 99% of the atoms. The technique is based on the principle that unexcited atom in the flame, that means 99%, are available to be excited through the light beam by observe the light specific wavelength of the required element. Each and every element having the separate specific fingerprint wavelength also. Each and every atom. Okay. So suppose we are analyzing the sodium, in sodium having separate halide cathode lamp, sodium having separate wavelength. From that halide cathode lamp, we are producing a light beam that light beam passed through the flame, that whatever the atoms present in that flame, that was getting excited. Suitable element. That means, suppose we are producing the hallowed cathode ray of sodium, the sodium atom only excited from the flame. The light source is used in, and a light beam is directed through the flame. The experiment is a Beer-Lambert's law, or known as the Beer's law experiment. Okay, and metal ions in a solution are converted into atomic state by means of the flame. When the light is of the correct wavelength is supplied, the amount of light is observed is measured and the reading for the concentration can be obtained. Okay, that means when light of the correct wavelength is supplied, the amount of light observed is measured, reading for the concentration can be obtained. So I will explain further in the next slide. Okay, this is the example of the Beer-Lambert's law. Beer-Lambert's law. That means this is a cuvette. The intensity of the light in and transmittance of the light out. This is the path length. Here path length is the flame. Burner is the path length. Okay, and absorption takes place. See, in incident light beam dense means darkness, and existing means transmittance light intensity. Means the metal ions present in that cuvette that was absorb the light. This is the tool to find the concentration. That means, suppose, see, pure water is placed in that cuvette, you will get the same reflectance, transmittance. Suppose sodium or any other metal is present in that cuvette, that will absorb by the light which was already passed. According that light intensity and the transmittance, which was incident and transmitted, we are calculating the concentration using the A equal log base 10 of the I0 by I epsilon CL. Here, say epsilon is like epsilon, and this is a observability constant, and this is the concentration, this is the length of the light passes through, length of the light. This is the basic fundamental of the atomic absorption spectroscope. See, typical animation picture of that, how the atomic absorption is working out. Okay, the input sample, this is the nebulizer, and the light is passing through the flame. It's a detector. See, automation is carrying and further is absorbed. Then after absorptions, detector will detect the transmittance of the light. See, what is the meaning of automation? Converting the metal ion into the free gaseous phase state atoms. Gaseous phase. Automation means source of the thermal energy needed for conversion of the ions in solution, atom in gas phase. Means atomization, where atomization occurs, that is the automation. Atomization means converting the gas phase molecule to gas phase. Okay, then we will go for the important features of the AAS. What are the parts? This is the nebulizer is an important role. Nebulizer is the heart of the AAS instrument. Nebulizer is the heart of the AAS instrument. Most of the chemical process takes place in that atomizer, means in the nebulizer only. Okay, so now we are going for nebulizer. Okay, nebulizer is the highly important in the flame atomic absorption spectrometer. Okay, this is the burner, this is the nebulizer. See, this is the nebulizer. Here we are introducing the sample and fuel. See, here sample phase is changing here only. After phase changing, it was entering with the mixer of fuel to the burner. Okay, most complicated in the instrument is a nebulizer. nebulizer converts the sample solution into mist or aerosol. This is the mist and aerosol. This is the nebulizer. This part I was zoomed out with the image. This is the mist or aerosol. Mist and aerosol means water droplets is present there. This is then forcing the sample with high velocity. Forcing the sample with high velocity. Forcing the sample with high velocity, we will get the like this mist or aerosol. Then the mist is mixed with the fuel, means accident. Say fuel mixed with the fuel and accident. The nebulizer sample mixed with the fuel and accident, then carried into the flame. Flame is already existing there, and sample aerosol mist is mixed with fuel, then further introduced into the flame for the flame purpose. See, again I was showing that. For example, this is sodium cathode lamp. This is the sodium chloride solution we are introducing, and sample here we are getting that aerosol, and further we are aerosol is mixed with that fuel and oxidizing gas. Then the droplets again is converting the phase, means solid, liquid, gas phase. Solid phase converted to liquid, liquid to gaseous phase, and further introduced into the flame. Okay. So working flow of the AIS is liquid sample is shuttled. Sample passes through the plastic tube into the flame. Flame breaks the molecules into atoms. Monochromator selects the wavelength that reaches by detector. Concentration of the element is measured by the emission, absorption, or radiation. Concentration of measured at ppm level as well as ppb. Parts per million and parts per billion. Okay, means this is the microgram, this is the nanogram level. So here I was showing flame atomic spectroscopy. Overall mechanism means first sample, then nebulization forms a mist. In the nebulization forms a mist, dissolution forming the solid and gas aerosol, volatilization like gaseous molecule, and dissociation into atoms. Okay, see. First nebulization, desolvation, liquefaction, and vaporization, and automation, excitation, and ionization. This process occurring during the process in the nebulizer. Okay, and through the flame. Same picture I am explaining through the graphically. The solution sample, nebulization, spray. This is the aerosol. Means this is the nebulizer spray. Desolvation, dry aerosol forming, and volatilization. Then free atoms. We are detecting the free atoms. Okay. Now I am going to discuss about the graphite furnace atomic absorption spectroscopy. Already I have explained you that. That means atomic absorption spectroscopy divided into two types. One is the flame atomic absorption, another is the graphite furnace. Okay. What is the difference between the flame and the graphite? Nothing but the flame atomic absorption spectroscopy. We are dealing with the flame only. Atomic furnace, graphite furnace atomic absorption spectroscopy, we are creating flame instead of we are using the electro-thermally we are automation. We are automation carried out through in that flame in flame absorption spectroscopy. In the graphite furnace, electrothermally we are giving automation. That means, see, the previous flame atomic absorption spectroscopy, in that screen, see this part will be removed. Totally, this part will be removed. See, graphite furnace. Okay, graphite furnace. So in that graphite furnace, from top onward, from top, we are introducing the sample. This is sample bed. Electrothermally, using the electrothermally, we are automation under the high temperature. Here we are not using that fuel in graphite furnace. We are not using the flame. We are using the electrothermally automation process. The graphite furnace will get the temperature electrothermally. Okay, this is the fundamental. And using the graphite furnace, we can go the below ppm level. That means nanogram level. We can try it. So we can analyze that accurately. Generally, atomic absorption spectroscopy, most of the people, they're preferring flame atomic absorption spectroscopy because of the repeatability and easy to handle. This is the versatile method, flame atomic absorption spectroscopy. Somebody they want in trace elements like mercury and prestigious elements, costliest element. On that cases, they are using the flame furnace only. For the research and R&D purpose and during the PG and the UG, so generally people are preferring only the atomic absorption spectroscopy only, flame atomic absorption spectroscopy only. Again, I am showing that. So before going to that study about and reveals about the atomic absorption spectroscopy, you can go to the earlier stage, the basic fundamentals of alpha principle, how is the exclusion, so what is the absorption, what is the emission, what is the movement, the electron movements from the ground state to the excited state. That means ground K shell to L shell, L shell to M shell. Okay, these are not the level. See, S1 level, S2 P2 level, S3 P3 D3 level. That means K L M N. This is the level. Alpha principle, I'm going to show you that this is general rules. Electrons fill the lowest energy orbital first. This is a Tennant rule. See, 1s and 2s. 2 comparatively, 2p is more energy than 2s, and 3s also more energy compared to 2s. Repeat, this is the energy level diagram. Again, you show that this is the electron configurations are for your understanding purpose. The 1s to 2s to 2p, 6 and 3s. Okay. So before going to the atomic absorption spectroscopy, and suppose you are doing work with atomic absorption spectroscopy, you can reveal those fundamentals that will more and most helpful to your furthermore analysis. Okay. So in that atomic absorption spectroscopy, there are the important parts. One is the nebulizer part. Another one is the anode cathode lamp, and third is the fuel. This is the three is very important, like computer, monitor, mouse, and keyboard, monitor, and CPU. Like same atomic absorption spectroscopy, nebulizer, lamp, and fuel. These are all the very important tool in the atomic absorption spectroscopy. Okay, halogen cathode lamp produces emission lines specific for the element. I already told you that sodium means sodium, iron means iron. See, this is the lead lamp. This is the lead lamp. Cathode is made from the element of interest. That means cathode is made from the element of interest. Means suppose we need iron, means this is iron cathode. Copper cathode, mercury cathode, arsenic cathode, tin cathode. Okay, cathode must conduct current. This is the anode cathode, that is the main source of the light. The light is passing through the flame containing atoms. That atom get excited through the light energy only. This is with the electrode. Only two type of lamp. One is this is the electrode-less discharge lamp. This is the electrode lamp. This is the electrode discharge lamp only. This is advanced method, and the salt of the metal interest is sealed quartz tube along with the inert gases. This is the containing inert gases. The RF coil, lamp containing metal salt. That means metal salt means sodium, iron, copper, cobalt, any as your interest. Okay, radio frequency fields exist in inert gases, excited gas metals. Light energy about 100 times greater than the gas. That means comparatively, the electrode haloed cathode lamp, electrode-less haloed cathode lamp, 100 times higher light intensity it was producing that. That's why generally we are using that electrode-less haloed cathode lamp we are using generally. Okay, this is a recent technology developed. Recent technology developed by the Instrument Analytical Jena. Okay, so many companies, so many manufacturers there. The Analytical Jena is a German-based company. They are developed specially xenon arc lamp. That means I already told that every time for every element you have to change the lamp, which was interest. Suppose you want to analyze iron, Fe, you can change that Fe haloed cathode lamp. Suppose you are interested in that sodium, you can go for the sodium lamp. And at that time, we can place the 6 lamp, but we can analyze only single element only. Means in that holder, at that time, we can place 4 to 6 lamp only. And we can analyze only one in at a time. So, in order to remove these difficulties, okay, so the company that is interested in xenon arc lamp, this xenon arc lamp is suitable for all the metal elements, which was mostly covered all the elements. Okay, this was producing wavelength range from there 190 to 900. This sunlight, this is a xenon arc lamp, and this brightness almost like the sunlight, like a white light. That is the main important properties of the xenon arc lamp. Means bright was like a sunlight. So we know all about the sunlight. Sunlight having that multiple. It was having that multiple lines. Okay, suppose we are passing the sunlight through that prism, we are getting that BIBZIA. Same fundamental, same like this xenon arc lamp having that spectral lines in itself, it having the spectral lines. So that's why we will analyze the 192 up to 900 of the particular metal element. So we can't change the lamp every time. It's not practically not possible. But in order to reduce the difficulties, nowadays technology development means now we don't want to change the lamp, so you can place a single lamp. You can analyze all the elements simultaneously. This is the easiest way to analyze. Deuterium halogen cathode lamp also we are using that. That means you reduce the noise only. Means reduce the noise only. That means those those elements having the wavelength of absorbance 190 to 320. During that analysis, we have to use halogen cathode lamp to remove the noise. So further again, the third important features is fuel oxidant of the AAS. We have discussed about the lamp, we have discussed about the nebulizer, then finally we are going for the fuel and oxidant for the AAS. See? The flame temperature is important. This is the true for both automation and excitation. Means for automation and excitation, we require the flame. All the flames requires both fuel and oxidant in order to excite. All the flames require the oxidant and fuel. Means oxygen and air is the oxidant. Fuel means acetylene, nitrous oxide is the fuel. In order to sufficiently atomize most metal ions and excite sufficient metal atoms for more easily excited element, means we have to complete concentrate. We have to analyze the complete concentration. We have to thoroughly, completely atomize all the atoms present in that solution. That means hotter flame is very, very important. Most common flame is air acetylene and air acetylene Air acetylene is a very common flame in the atomic absorption spectroscopy, which was producing the temperature 2300 degrees Celsius. For oxidant purpose, we are not using the oxygen because burning velocity is high. Burning velocity is high means, that means the flame is heavy rich. If the flame is heavy rich, the burning velocity is high. If the burning is rich, we cannot able to analyze the concentration of the metal ion. We have to control the flame. How can we control the flame? Means suppose the oxidant property is high velocity property, the oxidant having the high burning velocity, it is not suitable for the atomic absorption spectroscopy. This is suitable for only the building purpose only. Okay, for the analytical purpose, for the R&D purpose, we are not using the oxygen as an oxidant because we have to control the burning velocity. Simultaneously, we have to increase the temperature to achieve the good automation. That's why we are not using the oxygen. Generally, we are preferring the air. And oxygen with acetylene will give the high temperature, but that is not in use because of the high burning velocity. Instead of that place, nitrous oxide we are using as the oxidant in this case. Okay, the flame temperature, the choice is made upon that on which flame temperature burning velocity combination works the best the given element. So every element they are having a certain typical properties of the flame property. So already we are analyzed which flame combination will give the complete automation. That was shown in that already periodic table. Okay, in periodic table I already told you that 60 to 70 elements we can analyze. In that elements, most of the elements we will analyze, we can easily analyze using that air acetylene, and some of the elements we will analyze through using the nitrous oxide and acetylene combination only. Okay, this is the flame property of the air acetylene. This is the flame property of the nitrous oxide and acetylene. See, light means blue, dark blue is reduced, and this is the acetylene flow is increased for switch over to nitrous oxide. This is switch over during as air acetylene and converted into nitrous oxide acetylene. During that conversion, you will get the same like flame. The temperature chart I showed you that oxidant, say oxygen, air, and nitrous oxide is oxidant. Fuel is a natural gas, hydrogen, acetylene, natural gas, hydrogen, acetylene. See, these two laws below bottom two we are using. Burning velocity also you can compare it generally. Okay. So this is acetylene cylinder, this is pressure gauge to control the pressure, and this is air compressor. This is a typical picture for that nitrous oxide cylinder. These are properties of metal and non-metal. What is the difference? I will show you that. Okay. Generally, metal ions we are analyzing through that atomic absorption spectroscopy. Okay. So what is the difference? How it was getting dilution? I will show you that this slide. Okay. Now the mechanism part is completed. Now we are going for the standard sample preparation. How we are preparing the sample. The important, very, very important step in that session is standard sample preparation. Standard sample preparation is very, 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 very important step. Because that standard sample, the standard is tool, means standard means known concentration, is a tool to identify the unknown compound. That means from the weighing onwards, from dilution onwards, to introduce into the flame onwards, it is very, very important step. Okay, so nowadays the readily available AAS atomic absorption standard is readily available from the market. You can use, otherwise you can prepare from that molecule like sodium chloride, AgNO3. You can dilute, you can weigh and dilute preferably. So most of the guarantee period is only 2 years only. Okay, only 2 years only stock solution. Okay, you can try to prefer the stock solution in the 1000 microgram per ml, 1000 ppm. Okay, and maximum try to prepare every time in freshly. So fresh preparation and fresh calibration curve will give the accurate result. That means nearby your true value. Nearby your true value, you will get the result. Okay, this is a very, very important standard sample preparation. We have to concentrate that. Okay. And suppose you are prepared to the standard, you can store the sample in cool, you avoid the direct sunlight and store the cool place. Okay, for the short term periods, like the 1 week, you can use the 1 week. That is sufficient. It's selected metal only. Not this is the 1 week preparation, not suitable for the all the metals. Selective method only. Okay, means you are all aware about the preparation about the 1% solution, 2% solution, 1 molar solution, 2 molar solution, 1 ppm, 2 ppm, 3 ppm. This is very important. Generally, we are preferring the standard concentration 1 ppm, 2 ppm, 5 ppm, 10 ppm for the lower analysis. For graphic analysis, 100 nanogram, 200 nanogram, 500 nanogram, 1000 nanogram we are preparing. Okay. Suppose you are preparing the solution of the stock solution 1000 ppm, you can go for the serial dilution. Suppose you need your dilution concentration 1 ppm, you don't go for the direct preparation from 1000 to 1 ppm. Stepwise dilution is very important. That means 1000, 100, 10, 1. This will give the more accuracy and reduce the analytical error. You don't try directly 1000 to 1 ppm. It may reduce your solvent, it may reduce your time, but it simultaneously increase your error. Okay, so you can go through that protocol, means stepwise dilution with required concentration. And the maximum stock solution of 1000 ppm, you can prepare with the 0.1 molar nitric acid. This is safe for you, as well as 0.5 nitric acid. So you can keep your standard up to 1 week or 10 days. So this is the calibration curve. See, first day we are analyzed, we are getting straight line, and second day, third day, fourth, fifth day. That means concentration of iron present in that standard, it was getting reduced day by day. Suppose you are preparing the standard in that acidic medium, it will not get reduced as soon as. Suppose you are preparing in that standard in that water medium, it will get reduced. Okay, maximum try to prepare the stock solution in acidic medium, and serial dilution also try to perform that acidic medium only as possible. So I already told you that diluted octane 0.5, 1.5. So maximum metals means very dangerous metals like mercury and arsenic, lead, cadmium. So we will analyze the 0.5, 1 and 1.2 ppm. According to that, we can paper. Suppose sodium, calcium, we are analyzing that. You can go for the 10 ppm, 20 ppm. Whatever your requirement. What is your requirement? According to that, you can go for that preparation. See here that from the slope, 0.5 ppm solution showed the concentration drop after 1 hour. After 5 hours, 0.5 1 ppm solution showed concentration drop almost half values. Almost half values. That means I am already told that you can every time you can go for the fresh preparation. Every time you can go for the fresh preparation. That fresh preparation will give the accurate result nearby your true value. Oh, okay. How we are comparing the standard sample? Okay. See, this is the standard plot. This is the sample plot. See, this is a sample. This is the sample dash. Okay. This is the standard. 4 standard here we are used 4 standard, and unknown sample we are spiked. Means it was showing the absorbance. The absorbance is calculated against the standard concentration, standard absorbance. Then it will show the result.
See, in this case, see, comparatively, this unknown sample is away from our standard curve. Note this point. This means the standard curve, unknown sample, we are getting outside the curve. In this case, the two suggestions is followed. One is, otherwise you can reduce your standard according to your sample, otherwise increase the sample concentration. So two option is there. Generally, you can go for the lower dilution of the standard if possible. Suppose you are having more sample, you can increase the concentration of the sample and get to back into the mid of the curve. Means if you want the accurate result, you can almost try with the mid of the curve of the standard. Here you will get the correct slope value. Okay, means always your unknown sample, always try to follow and fall mid of the calibration curve. This is very, very important. And this is the example for how we are preparing the standard sample solution and standard AgNO3, how we are preparing that, how we are weighing. And aluminum, how we are preparing the 0.575 gram of silver nitrate, dried 110 degrees Celsius in oven, dissolved the nitric acid and diluted with the nitric acid, 0.1 molar, and dilute up to 1000. It will give the 1000 ppm of the silver. And aluminum, same as aluminum. Aluminum here, pure aluminum metal we are using, that not salt we are using. Okay, this is the example. And manually, how they are calculated 1.575. Here, the mentioned 1.575 of gram of silver nitrate dissolved into 1 liter of the solvent will give the means 1000 ppm, means 1 milligram per ml. That means 1000 ppm of the standard. How it? That means, see, 1.575 gram. See, atomic weight of that silver 107.8682, nitrogen, oxygen, total. This, see, 1.63 gram of AgNO3 contains 1.073 gram of silver. Okay. Therefore, 1 gram of silver containing 1.575. See, this is the 1 ppm. This is the calculation. How we are calculating it. You can go for the back calculation also. You will get the same answer. That means 1.575 gram is AgNO3 is dissolved into 1 liter of the solvent will give the 1 milligram per gram. That means 1000 ppm of the or 1000 microgram of the solution concentration of the silver. This is the method of calculation. And where it was uses of the areas. Drinking, environmental, drinking water, sludges, soils, semiconductors, nuclear environmental, metals, earth science, life sensor, blood, urine, drugs, tissues. So generally, yes, nowadays we are using all the fields where it's necessary to analyze the elemental. Mainly in agriculture, mainly in the food industries, mainly in the water and drugs and pharmaceuticals. These are all the very important field we are using the atomic absorption spectroscopy. And question and feedback is also welcome. So this is my mail ID and contact number. So if you have any doubt, if you have further any assistance, you can contact through the mail as well as contact number. Thank you very much, you all, for your sincere passion and kindful support. Thank you very much.
Thank you, sir, for your wonderful explanation about the theory instrumentation of atomic absorption spectroscopy, plain atomic absorption spectroscopy, graphite furnace atomic absorption spectroscopy. So there is one question in the chat box. I shall read it.
Ji, madam. Means.
Can you please mention the AAS specification, model, and cost of the instrument, and the supplier for the good instrument. Very nice session. Thanks for the speaker and the organizer. There is a compliment from Dr. N. Vijayakumari, Assistant Professor, Salem. I shall read the question again, sir.
Okay, madam, means I can't able to see the screen, madam. Once again. Okay, madam. Thank you, madam. I'm very pleasure to. Okay, madam. Thank you. I'm very pleasure to answer your question. So, mention specification and model and cost of the instrument of the supplier. Good instrument. Okay. And for my suggestion, specification is very lengthy one. Okay, this is a technical specification. Okay. Hello. Hello.
Yes, sir. Yes, sir.
Madam, can you able to listen my voice?
Yes, sir. Yes, sir. We are able to listen.
Okay, madam. The cost of the instruments, more or less, I think 20 to 30 lakhs only, madam. 20 to 30 lakhs only atomic absorption spectroscopy flame, not graphite furnace. Okay, madam. And thermo is wonderful, madam. Thermal is very nice. This is my experience. Thermal is very nice, and you can try with the thermal, madam. Okay. And specification means how many elements of your requirement. How many elements? That is very important. And the latest model, ICE model, is sufficient for us. Means for the academic purpose, ICE model is very sufficient. Okay, madam. And specification means how many elements you are going to analyze, how many lamp at a time, your requirement, lamp requirement. These are all the very, this is a very important parameter before purchase. Before purchase, that means number of lamp, very important, and manufacturer is a thermo. The cost of them is around 20 to 30 lakhs, madam, only.
Okay, sir.
I think.
Thank you, sir. The next question is from Selva Kumar. What is the reason for the metal concentration is reduced day by day for water solution?
Okay, madam. Very good, nice question. The pH of the water, that means we are maintaining the neutral, as well as sometimes it was getting that interaction with that ambient temperature like air contamination. So the property of water, that means acidic nature of the water get reduced towards the base. That's why I'm telling you that. That means try to prepare your strategy in acidic medium. So acidic medium will keep your concentration sustainably up to 1 week. Selective metals, based on selective metal. Water, suppose you are storing the solution, in storage also very important, in open place, not controlled in the room temperature, not controlled the humidity. Definitely it will get reduced. Suppose you are controlling the temperature, you are controlling the humidity, it will not reduce as soon as. And the water is react with the air, open air. Okay, it will automatically get reduced in the pH, it will get changed, and carbonation it will be formed. This is the meaning that CO2 will interact with your water, and automatically pH will get changed. The pH is, once your pH is changed, that means automatically your concentration will reduce. That is the reason. This is the reason, Mr. Selva Kumar. Okay, madam. Okay. Then I will go through how to calculate the actual concentration of the metal from the real concentration of air. Any problem to have the absorption value less than the 0.1. Absorbance value. Madam, kindly read the question, madam. If any problem to have.
Is there any problem to have an absorbance value less than 0.1 in AAS?
No, madam. Okay, absorbance less than 0.1. Okay. Suppose here is a calculating real concentration. Yes, is any problem they have absorbance? You are asking about the absorbance. Okay, madam. Generally, we are getting that absorbance also in low ppm. We are getting the absorbance less than 0.1 also. Only thing is, we have to get linear range and accepted range of the instrument. Each and every instrument and each and every element, they are having the acceptance range. From that range only we can analyze the element with high values, means high end values. We will get the accurate, nearby accurate values. Suppose you are analyzing below 0.1, means we don't go for below 0.1, means that means this below 0.1 not same for all element. The lower concentration may vary every element and every wavelength. Each and every element, they are having two different wavelengths. One is primary wavelength, another one is a secondary wavelength. From the primary wavelength, you will get the almost high absorbance. But secondary wavelength means, suppose you are analyzing the lower concentration, suppose you want to analyze a higher concentration, you can go for the secondary wavelength. During the secondary wavelength, okay, madam, you can go and analyze, but you have to get the linear curve. So, and with the recommended range of the instrument. Means whenever you are purchasing the instrument, that purchasing time, the suppliers, they clearly explain you that what is the range of lower, what is the high range of the element, you can analyze that. According to that, you can go your preparation. Means linear range is very important at any concentration. Okay, madam. Thank you.
Thank you, sir.
Okay,
There's a question from Sandeep Sangaran. Is auto sampler present in modern models of AAS?
Yes, sure. Nowadays, auto samplers are working there. Okay. Only thing is auto sampler and auto diluter is there. Okay. And this is a very important thing. Is this is we are doing with the flame, and we are doing the dangerous gases also. So presence is very important. Auto sampler, suppose we are using the auto, we are having continuous sample. We are saving. Suppose you are using the single sample. Now, suppose you are in the water industries. So you are producing water. You are in packaging water. You are working in packaging water. You are working the drinking water. You are working the commercial water. Okay. In that case, you can use the auto sampler. You will get a wonderful result. Suppose you are in the R&D institute. You are in an institution like college or universities. You are handling multiple samples, multiple elements, multiple concentration. In that cases, auto sampler is not good, as per my advice. You can procure, but at the time of element, at the time of sample matrix, you can decide whatever suitable. Okay. Yes, nowadays modern instrument having auto sampler. Myself, I am having also auto sampler, but we are not preferring the auto sampler. Thank you.
Next question is from Jennifer Nister. Is there any recommended procedure for sample digestion of biological samples?
Yes, definitely. For AAS, main thing is the standard preparation. Another one is the sample preparation. Okay, especially biological sample. For biological sample means one thing you can remember once again. Even biological sample, you are analyzing only the metal. Okay, you are analyzing only the metals. Okay, try to digest your biological samples in that aqua regia or in 1 molar nitric acid medium under hot plate or using the water bath. Okay, madam, this is the easy way to digest. Okay, according that your biological sample, you know about the safety precaution. You know about the sample. You know your experience about the sample. What is the sample nature? Okay, according that you can decide yourself. But digestion must be done through only the aqua regia, otherwise nitric acid or otherwise 1 molar nitric acid is sufficient.
So next question is, which is more suitable for biosorption studies?
Biosorption studies. AS
or ICP, OES?
ICP-MS is okay. ICP-MS is okay. The biosorption studies, ICP-MS is okay.
Thank you, sir. Some of these samples are not dissolved in water or acidic medium. Then what are the other solvents can use? This is a question from Dr. A.S. Ganesh Raja.
Okay. So thank you, Dr. Ganesh. I'm very proud, very happy to answer this question. So don't worry. Suppose your sample is not dissolved in that water or in acidic medium, try to perform in hot plate. So most of the sample in acidic medium, especially acidic medium means you are using, I think you are used nitric acid or hydrochloric acid. You can try with aqua regia. Aqua regia is a wonderful dissolving agent for AAS. Suppose in that aqua regia also you are not getting dissolved. You can place in hot plate for 1 hour, 2 hours, 3 hours. So definitely you will get the solubility. Nothing to worry. Definitely you will get it. Okay. Thank you.
One more question from Vijay Kumari, madam. Is there any availability of multiple source of lamp? If available means, what is the cost?
Yes, definitely. Xenon arc, already I told you that Xenon arc lamp is the available multiple source of the lamp. Okay, but this cost is very too cost. Only analytical xenon means, madam, you can kindly note it out that analytical xenon. This is a German-based company. The headquarters is placed in the Delhi. Okay, they are only developed the multiple source of the lamp. The lamp is cost highly cost. Means in India only 2 or 3 people they are having on person. Okay, means yes available, but academic level is not possible, I think. Okay, madam. Thank you.
Next question is from Jemima, madam. What way AA is different from flame test?
Flame test. Okay, very nice question. Certainly, the flame test means we are well vessel like flame photometer. We are doing sodium, calcium, potassium means group 1 and group 2 elements we are doing. Okay, only not more than beyond. Okay, and the concentration also not that much accuracy comparatively in AAS because automation is very important, complete automation, and thermal flame temperature is very important. For flame test, we are not that much level temperature we are having. We are using only simply natural gas only. Okay. So you are not getting complete temperature to break the atoms in that molecule. That's why you will not get the correct concentration. That's why comparative flame A is very good. Thank you.
Thank you, sir. Next question is for protein sample and leather sample. What are the parameters need to be taken care of for sample preparation?
Okay. For leather sample, protein sample and leather sample. Okay. See, leather sample generally chromium rich content. Chromium is rich in that leather sample. Okay. Leather sample. Hello. Hello.
Yeah, yes, sir. Yes, sir. Yes, sir.
Okay. For leather sample, general chromium is in rich for leather sample. And protein sample, protein will not interfere. Protein will not interfere with your observers. But in leather sample, metal is means other metals like chromium, lead metals are present. I think highly. Sometimes it may interfere with your flame, and it will difficult to cover your concentration, difficult to analyze your concentration. Sometimes with your sample matters. What we can do? So you can go for the dilution. You can reduce the chromium level. If possible, you can suppress your chromium using the other suppressing agent. So I'm discussing that here. Suppressing agent is also there. Suppressing agent means we can suppress other element which you are not interested. For example, you are interested in iron. Suppose the sample containing other than iron, you can suppress the other element using the suppressing agent. Okay. In protein sample, I think protein is not much more difficult. It's not difficult one, but leather is very difficult, and you can suppress using the suppress agent, and you can go and prepare and filter the solution clearly. Means before introducing the solution, clear, transparent, unturbid solution is very, very important. According to that, you can prepare the sample solution. For protein sample, if you want the protein sample, the main parameter to reduce the protein level, and you can extract the matter from the protein and extract using the acidic medium. Thank you, madam.
Thank you, sir. So the next question is, what about insoluble samples?
What about the insoluble samples? Insoluble sample means here discussing about the already from the national college also same question they are repeated. I think insoluble sample you can try to, suppose we want to analyze Okay, so many alternative method is also there. From the means the derivation method and the solubility method is other more methods nowadays. Developed method is also there. So from website and we will get the clue is also there. Solubility. How we will increase the solubility. Suppose you are not getting it insoluble, you can try with post-solvent. Synergic effect you will apply. That means, suppose we are trying with a single solvent, suppose you can increase the acidity range. Means pH, you can reduce the pH range. Sometimes it will get solid. Otherwise, you can increase the temperature. Means you can go for boil it. You can go for boil it. Okay, it will get dissolved. This is this. Otherwise, derivation means you can add furthermore. Like a suppressing agent, dissolving agent is also available. You can add, it will get dissolved. Thank you.
So the next question is from Heyman. What do you think about single continuous lamp? About what you saw, how its work in lower wavelength like elements arsenic?
Okay. Single continuous lamp, Mr. Heyman. Okay. Single continuous lamp. That single continuous lamp is single lamp. We are using that. That means we are not. What is the single continuous lamp means? Single lamp suitable for the all metal elements. Single lamp. This is not hollow cathode lamp. The continuous lamp means xenon arc lamp. Okay, like AS, like element AS. Okay. See, madam. See, Mr. Hemant. My answer is my genuine answer is. That means comparatively, the single lamp, accuracy of the single lamp is not satisfactory level comparatively individual lamp, individual hollowed cathode lamp. Because suppose you specializedly, if your specialization is arsenic, so you are selecting the arsenic lamp, hollowed cathode lamp independently, means in that cases, you will get the almost nearby true value. 95% confidence level you will get it. Suppose single lamp means xenon arc lamp if you are using single continuation lamp. Other metal ion interference also possible and the lower range of detection is poor in that case. So that's why for the lower concentration purpose you can for the specialized lamp like same electrode or electrodeless hollowed cathode lamp is okay. Thank you.
Sir. It's agreed from the chat box.
Okay. So what are the procedures for the sample preparation for food samples? Okay, madam?
Yeah, yes, sir.
Yes,
Sir.
From Arun Kumar. Okay. The sample preparation of food and proteins means nothing to worry. There is no precaution. Okay. Only thing is you can first dilute. You can extract the sample from the using the water or acidic medium or aqua regia or 1 molar nitric acid, etc. Okay. From that you can go for filtration or centrifugation using the 25,000 RPM. Okay. Get to back. Sometimes suppose you are using the filter paper to filter the sample for biological sample or food sample. Okay. You can confirm the filter absorbent property also filter paper. Better means sometimes filter paper will absorb your metal sometimes. So you can use suitable filter. Otherwise, you can go directly centrifuge under high revolution, high RPM. Means around 25,000 RPM of ultra centrifuge RPM. That is better for food and drug samples and protein especially. Thank you, Mr. Arun.
Thank you, sir. The next question is from
interpretation
madam.
of yes, madam.
Yes,
interpretation of results AS, which value we can use either concentration or absorption or actual concentration value. Okay, very good. Interpretation purpose that means we are using the known concentration. Well, we are first placing the blank. Okay, means auto zero for getting the auto zero like UV. Then we are placing the standard. We are knowing the known we are knowing the concentration of the standard and we are getting absorbance. Okay. And actual concentration means the actual concentration is the term is suitable for the unknown sample only. That means unknown sample, it was giving, suppose you are placing unknown sample into the AAS, you will get the absorbance. That absorbance is directly proportional for the sample concentration. Okay, that concentration is again further compared with that standard absorbance with standard concentration. You will get the actual concentration. That is the term of actual concentration. Okay, the actual concentration means after the comparison with your standard sample and the exact value of your exact value and exact dilution. Very, very important. Dilution factor. After the application of dilution factor and weight, you will get the percent in pp. That is the actual concentration. Means after the correction factor of dilution and the sample weight. This is the term of the actual concentration. Thank you.
So the last question is from Kritika Rani madam. How many standards are available?
Madam,
how many standards are available?
How many standards are available?
Yes,
how
sir.
many metals we can analyze that much standards? How many metals? Means 60 to 70 metals we can analyze. Okay, madam? That much standard available. Only range is the cost is different. Means suppose if you are interested to analyze this gold, this gold standard is very high, means around 15,000 something. Okay, you will get all the standard except the radioactive standards, non-metal standards you will not get. Okay, other all metal standards available in the market, different rate factor. According to that value of your metal and the cost of the metal is directly proportional for the rate of the sample. You will stand.
Thank you, sir. Thank you for your so you patiently explained all the questions. Thank you very much, sir. Also, you explained the atomic absorption spectroscopy in a very well manner. And I take this opportunity to propose vote of thanks. I thank God Almighty for His mighty presence in this webinar. And I am grateful to our beloved principal and secretary for his valuable, invaluable guidance even during the pandemic days. Also, I thank him for his gracious inaugural address. And I thank today's chief guest, Dr. Radhakrishnan and Mr. Saravanan sir. Both of you well explained, and the webinar brings a wonderful one, as well as the all the students as well as all the participants are benefited. And I thank Dr. Jemima Balasuli Juliana madam, the director of ACCIC and the convener of this webinar, for her tireless effort in the successful conduction of this webinar. And my sincere thanks are to Dr. Nazira Banu for her arrangement. That is, she contacted the speakers through the mail, and she took effort in bringing this webinar, and I thank her. And I also thank our faculty member, and my special thanks are to our Basa madam, who is behind us, always guiding us, and for her direction towards this type of conduction of webinars. And also, once again, I thank my faculty members. Also, I thank the participants. Without you, this webinar will not be a successful one. Thank you very much for your patience till from 10:30 to 1:45. Thank you very much for your patience. Thank you, one and all. Thank you, sir. Dear participants, please fill up the feedback form, submit it. It will be open only up to 2 o'clock. Thank you.
Jansi?
Ma'am, shall I end the session, ma'am?
Hello?
Ma'am, session end பண்ணிடலாம். கேக்குது ma'am, session end பண்ணிடலாமா ma'am?
Okay, bye, end பண்ணிருங்க. Thank you so much.
Thank you, ma'am. Thank you, ma'am.
அந்த ஈவினிங் ஒரு லிங்க் கொடுக்கணும்பா.
Okay, ma'am.
4 o'clock rehearsal.
Okay, ma'am.
Okay. Thank you, pa. Thank you.
Thank you, ma'am.